Hello. Hi. I'm just setting things up. Okay. Thank you very much for joining this early. Yeah, I'm just gonna announce it in my Discord that I'm alive. Not I'm alive. My goodness. Sorry. I'm going live on YouTube. Of course I'm alive. Hi. Good evening. Hi, Robin. You're welcome. It's a pleasure to hold streams. So, how is everyone doing? Did you guys? I guess it's it's a fact that most of my viewers are Americans. Hey, hi Christian. Thanks very much for joining the stream again. According to YouTube analytics, my biggest demographics are from the U.S. are based in U.S. So hope you guys had a great 4th of July. It's actually kind of crazy that the measure theory stream I had last Tuesday, it's not even a week, has already gained 11K views, which is insane. A almost 5 hour stream on beginning measure theory. Hi, Robin, Canadian. Wow, nice. Hope you had a great Canada Day. I'm in Canada too. So I was talking about the measure theory stream that I had on Tuesday. It got over 11K views, which is insane. It's like completely unedited raw footage of a 5 hour stream. And, you know, there, there are videos on lectures of measure theory uploaded by professors who that hasn't gone that many views for years, so which is very surprising. So definitely, the measure theory stream is now made regular, and it's going to be a weekly thing every Tuesday. And I apologize in advance that I cannot accommodate every time schedule preference, time zone preference. Right. I've seen comments that says, "Oh, it's a shame that I can't join it because I'm in Europe or something like that." Yeah, I'm sorry, but I can't do anything about it. Okay, so it's 8. Let's get started. I mean, more or less. I mean, formally, not formally, but we're not going to dive into the math right away. But we would like to move things towards that direction. So, as the title suggests, we're going to talk about mathematical statistics and exterior ballistics tonight, or whichever time for you. So, why are we placing those two seemingly disconnected subjects together? Of course, mathematical statistics is perhaps more widely taught than exterior ballistics. Mathematical statistics is widely considered a civilian topic, whereas exterior ballistics is inherently linked to the military-industrial complex. Why do we put these two subjects side by side? Well, the reason is quite simple. It's because I would like to kind of force a reckoning about the moral accountability of science practitioners. This was stated clearly in the announcement. What do we mean by that? Ballistics go boom. Oh, hi, inventive. Good to see you again. So, I'm not going to dance around. This position, I think, is, I would say, a challenge. It's a position that challenges the dominant view that scientific progress is inherently a good thing, and also perhaps science on its own is innocent and it's neutral. It's value neutral, as they say. A position that I personally, let's be honest, disagree with, and would like to force a reckoning. So, exterior ballistics is uncertainty is uncertain. So exterior ballistics is a clear case of how mathematics was developed in a way that is intrinsically tied to state power. And that's not a singular fact. Throughout centuries, mathematics has always been tied to state and corporate power. And, even some mathematicians nowadays and historically warn about this quote-unquote militarization or weaponization of mathematics. Although their sentiment and point of view are certainly valid, I would argue that the math we learn today is a civilianization of what is historically a weapon. So weaponization, although it's a fair warning, but it's actually historically inaccurate. Right? Exactly, it's right in the name, state. So I was saying, even though there's mathematicians who warn about the weaponization or militarization of mathematics, I agree with their sentiment and their warning, but it's actually inaccurate because most of the math we learn, especially in the applied stream, is a civilian retrofit of what is historically a weapon or a weaponizable asset. It's just the way it is. So exterior ballistics historically is a sister discipline to celestial mechanics. Right? We all know that Newton revolutionized celestial mechanics in his Principia. But if you look at the part 2 of Principia, part 2 of the Principia has not much to do with astronomy. Instead, it has to do with air resistance and the motion in a motion of particle in a resistive media. And we all know what that is about. All right. So, another example which weapon. Do you have an example? I was talking about exterior ballistics. That's because without mathematics to back up the military-industrial complex, a weapon, a piece of weapon, a hunk of iron is just a hunk of iron. Right? If a weapon cannot tell where it is fired at, then it is next to useless, right? So the subject of exterior ballistics is as lethal as an actual bullet, right? Because if this subject does not exist, then the deadliness, the sheer deadliness of modern warfare would not be a reality. Right? So I would like to force a reckoning that whether the development of science on its own is an intrinsic good, and whether practitioners of science themselves holds moral accountability, which in my opinion, yes, but I will leave that as an open discussion. I would like to start that discussion to be frank, because I don't see this being discussed very often in academia or in industry. Right? So I will perhaps for people who have joined the stream before, this is redundant, but I'm going to read the first paragraph of the preface by Exterior Ballistics, written by McShane, Kelly, and Reno. McShane, Kelly, and Reno, especially McShane and Kelly, were very widely recognized analysts and topologists, and they helped the U.S. government with exterior ballistics and just overall military efforts during the Second World War. And this is what they had to say. As a rule, the authors of a scientific book presumably hope that it will prove useful. The authors of this book wish devoutly that it will turn out to be quite useless, and that the application of exterior ballistics with lethal intent may cease. Nevertheless, it is clear that armies will mass and nations stand in readiness for war until Homo sapiens succeeds in better deserving his self-bestowed name. While this endures, there must be many who know something about the flight of projectiles, and a few who knows much about it. For these, this book is written. Okay, so it started from this. The book is began with a rather somber tone. Okay, so as far as mathematical statistics is concerned, it can also be weaponized. It lies at the heart of modern surveillance state and social engineering. Right? Of course, it is also a force of good. It lies at the heart also of advanced medical research, for example. So I'm trying to say is when you became an expert in mathematical statistics, people will queue up on you for your time, and they will tell you that what you do is making the world a better place, a safer place. In which case, you should really ponder on their intention. Okay. Anyway, so let's begin with the main subject. The first part of the main subject, the statistics part. Let's take a look at where we left off with last time. So last time we talked about survey sampling. So survey sampling is a very common method for empirical studies. Okay, so we talked about there are different types of study. I would challenge the premise that the study of ballistics is as deadly as a bullet. It informs the bullet fired to be more accurate. Consider the no effort case. It's better to have a gun and not need it than to need a gun and not have one. Nice. So yeah, I was talking about the we finished last time's mathematical statistics stream on the part of survey sampling. All right, so survey sampling is one of the three major types of empirical study. One is observational study, second is survey sampling, and last one is experiment design. So these are three very different characteristics, even though they're mathematical machineries, such as calculating sample statistics and whatnot. have some overlap. The nature of those studies are fundamentally different. Right? So I posted a quiz in my community tab this week on sample surveying, survey sampling. I was asking if we sample from a finite population using the simple random sampling without replacement, are the observations identically distributed, and are the observations independent? And it turns out that only 30% of the respondents got it correctly, which is, in my opinion, a little bit insane, because this is such a fundamental concept, right? If you sample from a finite population without replacement, the observations are not independent. Okay. They are identically distributed, meaning their marginal distributions are the same, but they're not independent. The IID assumption, however, approximately holds when the sample size is much smaller than the population size. So in that case, IID becomes a valid approximation. Okay, and even though I tried to explain that as much as possible in the comment, a lot of people still seem unconvinced. So a video on that is coming this week, because this is as urgent as pretty much as the rest of the part of statistics, because a lot of the emphasis, I think, in university statistics focus on saying algorithms, on calculations, perhaps, okay, but not enough, in my opinion, on such fundamental concepts. Okay, it's common to start a university level question by stating, suppose x1 all the way to xn, our IID follows a distribution of a certain form, derive the MLE, something like that. But it is not often enough, in my opinion, to investigate whether IID assumption holds. Okay? And one of the scenarios that IID arises is in survey sampling, when you have a much larger population compared to your sample size. All right. So I think I will skip 5.5 today and go straight into likelihood inference. Straight into likelihood inference. So likelihood inference is perhaps the most dominating paradigm. Okay, this is not an algorithm. It is a paradigm. It is a way of thinking about statistical methods. Okay, and another competing paradigm is, of course, the Bayesian paradigm. Okay, nowadays Bayesian paradigm is more popular than compared to, well, it was like 30 years ago, perhaps. Okay, so Bayesian paradigm is now considered a part of the mainstream methods, mainstream methodology, mainstream paradigms, and in some parts of, it's fair to say that Bayesianism is perhaps even the dominant method in particular aspects of statistics. For example, I have a good friend of mine who worked in weather prediction, and he told me that Bayesian inference is the dominant paradigm there. Thank you, Robin. So this is, I would say, the two dominating paradigms in statistics. The nice thing, or the interesting thing about statistics is that statisticians, unlike mathematicians, don't even agree on what problem they're solving. Because in pure math, even in applied math, the problem is usually settled. Okay, the problem part, the problem formulation part, is usually settled. The controversies, if exist, are mostly about whether a result is correct and whether sometimes whether a formulation is a good approximation to reality, that sort of thing. But in mathematical statistics, often the difference is philosophical. For example, many of you guys may know Fisher. Now, marketing modeling makes widespread use of Bayesian methods. Exactly. So I was talking about Fisher, Sir Ronald A. Fisher. He was undisputedly the originator of maximum likelihood. Okay, so Fisher was a polymath. He was not just a mathematician and statistician. He also studied biology and other bunch of things. And his math wasn't always rock solid from a modern viewpoint, even by his contemporary standard. His math was not rock solid, but he had great intuition. Okay, and Fisher himself categorically rejected the Bayesian paradigm. So there was fierce controversy surrounding the foundations of mathematical statistics. And for a long time, that two schools refused to talk to each other, which did statistics no good. I think nowadays the discussions are more not just civil, okay, but more productive. So one thing I like about this book by Evans and Rosenthal, is that it covers two paradigms roughly equally. See, the lengths are at least mostly equal, which gives the beginner a choice. I wasn't given, Fisher made the t-table exactly. I think it's fair to say that Fisher was racist. There was controversy surrounding that too. Yeah, let's not shy away from that. So Fisher was accused of being a racist due to his work in eugenics. Okay, something that was popular, and not just in England, not just in the UK in the early part of the 20th century, but throughout Europe. And of course, we know where such things saw its most abhorrent form. Right? So, scientists aren't necessarily saints. Okay. It's important to acknowledge their contributions, their originality, right? Their honest work, but it is also important to see their work from a critical lens. Right? Exactly. Right. So this is what I was talking about, right? So and statistical method was developed with sometimes dubious intent. So it's really is it fair to say that these methods themselves are value neutral? Do they not reflect human priorities and values? In my opinion, they do. Okay. So anyway, so be very careful. Do not fall easily into the trap that into thinking that science itself is neutral, because in my opinion, technical competence is incomplete, and you don't want to become a hired gun, simply a hired gun with a useful idiot, right? So you don't want to do that. Anyway, so let's go into the likelihood inference, the foundation of likelihood inference, 297. Okay, so on this channel, as you guys probably know, even though this is a math channel, a lot of the explanations, as I would like to think it that way, is that I don't want to dive straight into the math. I don't just want to dive straight into the calculations, the proof, and whatnot. Okay, I would like to spend time on the foundations, even for applied subjects like this one. Likelihood inference. So we have an outline here. Section 1 is the likelihood function. Section 2 is MLE, maximum likelihood estimation. Section 3, inferences based on MLE. Section 4, distribution-free methods. Section 5, large sample behavior of the MLE advanced. Okay, so this is, by the way, this book was intended as a first introduction to both probability and statistics, and perhaps introduced probability in a view that it will be used later in statistics. So it has a pretty clear objective when it comes to the arrangement of subjects here. It's okay to study the effects of race on employment, but it's not okay to study effects of race on intelligence. I completely agree. Let's just dive into the math. It's math more than time. Let's dive into the math. Okay, sure. Yeah. You know, I spend all that time, like 20 minutes, talking about values. It's the same purpose that a physicist walks into a lab wearing a hazmat suit. What we're dealing with here is not just a technical hurdle, but a subject of tremendous power. We don't want anybody to get hurt. In this chapter, we discuss some of the most basic approaches to inference. In essence, we want our inferences to depend only on the model P theta, where theta is in the set omega and the data S. Okay, so just a quick remark on the notation. P theta is a family of probability distributions. So a model here, the word model refers to a family of probability distribution, and it is indexed or parameterized by theta. Theta belongs to omega. I would like to mention that theta does not necessarily have to be a scalar, even though often in this course it is. Theta can be an abstract index, okay, and omega does not have to be a set of numbers. These methods are very minimal in the sense that they require few assumptions. While successful for certain problems, it seems that the additional structure of Chapter 7, Chapter 7 basically is on Bayesian method. I was saying that, or Chapter 8. Chapter 8 was on optimal inference. Okay, so likelihood inference is a approach. Okay, there is no a priori reason that this is the approach. It's very easy to get into the calculation when it comes to statistics, which is one of the reasons I love your geometric approach to stats theory. Thank you very much. And speaking of which, I really should upload a new video in that series. Okay, it's been a while. Thank you. But before doing that, okay, before talking about the geometry, I think I need to upload a video talking about the fact that the IID assumption I was talking about in sampling survey. Okay, why you have non-independence. Basically, I want to do a rigorous proof. Okay. The likelihood function, likelihood inferences are based on only the data S and the model P theta, where theta is in big omega. The set of possible probability measures for the system under investigation. Okay, so these are the inputs basically. The data, of course, is fixed, and the model is something that we assumed. So data is the reality, or the part of reality we choose to measure. There's a subtlety between that. Okay, data themselves aren't just realities; they are a part of reality which we choose to measure. And model are the random mechanism that we postulate generating the data S. From these ingredients, we obtain the basic entity of likelihood inference, namely the likelihood function. Okay, so let's define the likelihood function. The model is something we derive from math and logic. Yes, for example, the normal distribution, right? The normal distribution is, of course, a model. A family of normal distributions is, of course, a model. It has certain logic behind it. For example, it may arises from an IID random sum, like in the case of Brownian motion, or it can arise from rotational invariance. There is certain logic that gives rise to certain models because when it comes to practical applications, you got all these fancy formulas. Which one should you choose? Right? What justifies a normal model? What justifies a gamma model? And these are deeper questions. The mathematics for justifying certain modeling choices involves something called the what we call the characterization theorems. Exactly. It's important to realize how much subjectivity in choosing a model is. Yes. Yes, you're completely correct. So there is some math and logic is involved, but there's also subjectivity, of course. Yeah, and this is something that is hugely contentious because the whole reason that Bayesianism was rejected by the mainstream was the embrace of subjectivity. Right? The likelihood school, the frequentist school themselves, frequentist school were extremely critical about the Bayesianism because of the use of prior probability, right? So that's an explicit embrace of subjectivity into statistics, right? You're putting your personal opinion into influencing the data. And Bayesianism countered that by saying, well, you're using subjectivity anyway. We're just being honest about it. And so there was a huge controversy. Okay, when studying these things, it's important to keep that in mind and not treat these issues as completely settled. To motivate the definition of the likelihood function, suppose we have a statistical model in which each p theta is discrete. Okay, so now we're supposing that p theta is a discrete distribution, like a binomial distribution. Or Bernoulli, even simpler. Bernoulli theta. Bernoulli theta, theta between 0 and 1. This is, of course, a family or a set of random variables. Not random variables, but this is a family of probability distribution. Right? Each of them is discrete. It takes the values only 0 and 1. Given the probability function, f theta, here, probability function little f stands for the probability mass function, PMF. So f theta in this scenario is f theta of x is the indicator function x equals 1. It only equals 1 when x equals 1, otherwise it's 0. Yeah. Pure intuition influencing math. Intuition always plays a huge role in math. It's not just in applied math, in all areas of math. But the problem is, how do you justify that, and where do intuitions fall short? And it's actually hugely important. And perhaps we will see a video soon on the danger of geometric intuitions. Okay, sometimes geometric intuitions can gloss over important details. Anyway, here, let's continue. Having observed S, consider the function L. Dot stands for the variable in L, and slash S. Okay, so that's the notation for the function, for the likelihood function. Defined on the parameter space omega and taking values in R1, given by L theta given S equals F theta of S. So that's the definition. Actually, we have our notes here. Always ready to take notes. Suppose S follows p theta, which is discrete. It's a discrete distribution where theta is in big omega, with f little theta. Likelihood function is defined as such. That the likelihood function L theta given S equals F theta of S. So that's the definition. So numerically speaking, it is completely equal. Is completely equal to the probability density. So why don't we call it such? Why do we introduce this extra name? Well, the difference is in the perspective. On the right-hand side, typically, when we talk about probability function, the variable is s, whereas theta is treated as a parameter. In a likelihood function, however, s is treated as a parameter and theta is a variable. Okay, so that's the conceptual difference here. Difference. In probability function including probability densities and whatnot. So in probability function, s is the variable. Theta is constant or parameter. Okay, let's just call it constant. Okay, parameter has already has a name, has already a meaning in statistics. Let's just call it theta is treated as constant. It's like when we talk about f theta of x. Actually, you know what? This is wrong. My goodness, this is completely wrong. Let me just delete that. Okay, this is not correct. F theta of x is theta to the x 1 minus theta to the 1 minus x. Guys, I was stupid. Okay, f theta of x is this way. X equals 0 and 1. Okay, build your model from base axiom. I would say it is possible to take an axiomatic approach, right? Because you want to identify the most fundamental principles and avoid circular reasoning. All science attempt to do that in some way. Otherwise, science is it's a collection of information that bears no relation, right? Axiomatization is something that is science universally attempt to do. Even in fields like I would say perhaps in biology you would do that too. You want to identify the most important principle and discuss its consequences and compare those consequences, those derived consequences with reality, right? Like even in social science we do that. In economics we postulate that a consumer is an agent that minimizes cost or given a cost maximizing utility. Right, so these are axioms that aren't always easily verifiable, but we try to derive consequences from them. Right? These are axioms. The axiomatic approach is something universal, not just in pure math. Right? Even though economists wouldn't call their assumptions as axioms, more like working assumptions. Okay. Axioms are not sacred. Axioms are sometimes reverse engineered. You want certain results to hold, and you choose a parsimonious set of axioms so that it supports the result. Okay. Anyway, so I was talking about this definition here because this is absolutely crucial. The fundamental object of chapter 6 is this function. And the difference between a likelihood function and a probability function is a matter of perspective, even though the likelihood, let's just say, even though the numerical values are the same. Likelihood. The likelihood function uses theta as variable, whereas s is treated as constant. Of course, later when we discuss inferences, you see section 3 as inferences, we will consider s being a random variable. Remember, s is the data, right? So in that part, we will consider s being a random variable. But simply on its own, likelihood function is a function of theta, where s is treated as given. Right. So that's the conceptual difference here. So let's take a look at an example. Perhaps there's an example down in the text. Yeah, there is an example. So we will take a look at that shortly. We refer to L dot S as the likelihood function determined by the model and the data. So this is interesting. The likelihood function is determined by the model and the data. let's think about how do each component, how do each ingredient play that role. Why is L depend on the model? Well, from the definition, the model is P theta. P theta has probability function. In this case, we assume to be discrete, F theta. And L is numerically equal to that function, so of course the model plays a role. But why is it also determined by the data? Well, we substitute S being the observed sample. So the likelihood function is determined by both the model and the data. The value L theta of S is called the likelihood of theta. The likelihood theta. So the name is highly suggestive, right? So the name likelihood really talks about the likelihood of the parameter. The likelihood of the parameter, not the probability of parameter. So that's the important difference. We cannot talk about the probability of theta. Theta is just an index. In order to talk about the probability of something, that thing has to be an event, a set, or a random variable. Theta is simply an index. It has no underlying probability measure associated to it. Well, just a bit of a spoiler, in the Bayesian chapter, theta will follow a distribution called the prior distribution and also the posterior distribution. So you can see how fundamental the philosophical distinction is here. So in the likelihood function, in section 6, we treat theta that does not even have a distribution at all. This is something that is unknown, but is completely fixed. We do not even consider things like the distribution of theta here. In the Bayesian paradigm, we explicitly talk about the distribution of theta. Could we talk about the frequency of theta? No, not in chapter 6. Okay, within this, it's not absolute. Okay, so this is for this paradigm, for the likelihood paradigm, the frequency of theta, just like the probability of theta, makes no sense. Yes, this also means likelihood are equally important in Bayesian method. Bayesianism do not reject the likelihood function. It just thinks that it on its own is incomplete. Okay, and actually this notation, it uses a notation of conditional distribution, right? It uses a notation of conditional distribution. So in that case, this is already very suggestive. Bayesians tends to think about the distribution of theta given the data. A more orthodox notation for the likelihood function would be L theta semicolon S. So this way, the practitioner, the people who use this notation is saying S is a constant, theta is a variable, or at least theta is a primary variable, or S is a secondary variable. And they avoid this suggestion on conditional probability entirely. And here we're using that notation. Okay, so that's the philosophical difference. In chapter 6, we talk about likelihood of theta as a pure numerical value without assigning any probabilistic interpretation to it. We simply refuse to do so, because in this paradigm, theta is treated as a constant. It's just that it is unknown. We do not talk about the underlying probability measure for theta. Bayesianism openly do that in comparison. Okay, note that for the likelihood function, we are fixing the data and varying the value of the parameter. That's what I was talking about. Right, the perspective difference. Likelihood function, S is fixed, fixing the data, S is constant, and varying the value of the parameter. We see that F theta of S is just the probability of obtaining the data S when the true value of the parameter is theta. So this is by definition, right? Because here we're dealing with a discrete distribution. F theta itself, F theta of S itself is a probability. Recall, right? If X is discrete random variable, okay, Fx of little x is defined as the probability of x equals to little x. See here, this is exactly how we defined the probability function for the Bernoulli distribution. When x is 0, f theta equals 1 minus theta. When x is 1, f theta equals theta. Right? So theta is the probability of x equals 1. So, as we said, f theta of s mathematically is defined as the probability of obtaining the data when the true value of the parameter is theta. So this imposes a belief ordering on omega. So you're introducing a ranking system. You're introducing a ranking system on the parameter space. Which parameters you are more likely to believe? Likely. We believe theta 1 as the true value of theta over theta 2 whenever f theta 1 of s is greater than f theta 2 of s. Right. I think we touched on this and even showed example on this in the first stream of mathematical statistics. Right. So given s, so let's say the data is now observed. S is a fixed value we already observed. Right? If f theta 1 of s is greater than f theta 2 of s, this means assuming that theta 1 is the true parameter, the data has a higher probability to occur. This is what it says. So as a result, we believe theta 1 over theta 2 as a true parameter. So let's say if you only have two choices, you pick the parameter value that gives a higher probability such that the data occurs. This is because the inequality says that the data are more likely under theta 1 than theta 2. We are indifferent between theta 1 and theta 2 whenever the likelihood function are the same. The likelihood inference about theta is based on this ordering. Okay, so this obviously gives the natural method of maximizing the likelihood. So at the end of the day, when it comes to actual statistical calculation, it pretty much always boils down to an optimization problem. I was talking about the nature of statistics as a subject in the first stream, in which I declared statistics being a branch of epistemology dressed up in mathematical language. Epistemology, of course, is a branch of philosophy. Right? What is the nature of knowledge? What can we know and how we know it? Right? That sort of stuff. Right? Statistics is rooted in the epistemological thoughts called empiricism. But people like David Hume, who championed that observations rather than abstract thinking is the most reliable way to obtain knowledge. Right? So statistics is rooted in that tradition. And it uses mathematical language to organize a consistent set of principles to obtain knowledge. And the mathematical language typically boils down to two main branches. One, probability theory, and second, optimization. Note that this is only merely an approach to estimation. There's nothing inherently subjectively true about the likelihood principle. Exactly. It's an intuitive principle. Right? It is an intuitive principle. It is exactly as what Christian just mentioned. This is merely an approach. It's an intuition that seems to make sense. Okay, and if we suspend our disbelief on its potential pitfalls, we try to push as far as possible, right, about this methodology. Right? It's the most dominant method in practice nowadays, but its optimality is at this point at least unproven. In chapter 8 we will talk about certain optimal properties of the likelihood method. Okay, but right now we're not at that stage yet. There's nothing inherently superior about this procedure. Okay. So anyway, it's important to remember the correct interpretation. There you go, interpretation, correct interpretation of L as given S, L of theta given S. The value L of theta given S is the probability of S given that theta is the true value. Okay, it is not the probability of theta given that we have observed S. So it is not the probability of theta. The probability of theta, the phrase itself is nonsensical here. There is no probability of theta simply because theta has no probability distribution. Okay, theta is not an element of a measure space. Using the language of measure theory, we know theta comes from big omega here. A probability of theta only makes sense if big omega is a measurable space. Namely, there are subsets of omega which we deem quote-unquote measurable, and you can assign measures to them. We refrain from doing so right from the start. So the probability of theta is a cardinal sin. When you talk about probability of theta using the maximum likelihood method, that's a cardinal sin. This says the person does not know what he's talking about. Okay. There's no such thing as probability of theta in the maximum likelihood paradigm. It's not the probability of theta given we have observed S. Also, it is possible that the value of L theta given S is very small. Right? Of course, because remember, here S is the sample, right? We do not say S is a number or a set of numbers. In most situations, S is a set of numbers or a vector. So therefore, L is really the joint distribution. Okay, sorry, the value of L equals the joint distribution, equals the joint probability. And of course, we know if you calculate joint distribution, the more data points you have, the value of the joint probability tends to get smaller and smaller. Right? So it's possible that the value of L theta of S is very small for each value of theta. So totally possible, simply because when you have a large sample size, the joint probability naturally decreases. It's not the actual value of the likelihood that is telling us how much support to give a particular theta. Right? Let's say if you calculate the likelihood function and it turns out to be 10 to the minus 6, and you say, oh, that's too little, theta is impossible. Right? That's why the absolute value of the likelihood function is pretty much meaningless. The absolute value of the likelihood function is pretty much meaningless. The likelihood function itself is only a ranking. This is a ranking system. This is a ranking system over omega. So as with any ranking, the value itself is useless. Is inherently meaningless, right? So what we really care about is the relative likelihood. Right? Likelihood say if L is 10 to the minus 6. This says absolutely nothing. We don't know, is this a good or is this a high value or low value? Simply by looking at the number, this says nothing. You have to compare the likelihood value with other candidates. Right? This is a ranking system. So this naturally leads to the idea of a likelihood ratio and a likelihood ratio test. Relative likelihood ratio test, the LRT. Okay, so here in this particular section of the text, we define the likelihood function, and as we can see, we can already see from this verbal description why we're maximizing likelihood and why we're considering methods such as a likelihood ratio test down the road. Okay. They're not probabilities, which is the most confusing thing about likelihood. Exactly. Likelihood is a ranking system. This is just a ranking system, which happens to agree with the probability when theta is fixed. But the whole point of likelihood function is that theta is not fixed. It's a variable where S is fixed. Right. Anyway, here. I hope this gives the enough motivation for introduce this method and not just something that is pulled out as if from magic. Okay. So here is the last sentence. It says, it is not the actual value of the likelihood that is telling us how much support it gives to a particular theta, but rather its value relative to the likelihood of all other parameter values. So that's why we consider things like the relative likelihood and likelihood ratio, LR. Okay. Yeah. So yeah, I appreciate the discussion in chat because this is actually what like real discussion, real debates over the foundation of statistics look like. Okay. It's it borders it you see the discussion is rarely mathematical at all. See, just by looking at the chat, the discussion borders on philosophy rather than mathematics. Right? Because this is what statistics really is. It's a branch of philosophy that happens to be dressed up in mathematical language. Even though nowadays, if you pull up a statistical paper, it looks exactly like a math paper. Definition, theorem, proofs, lemmas, and stuff. But fundamentally speaking, it is not even mathematics. Okay, it is a branch of philosophy that is dressed up in mathematical language, which happens to be useful for science. Right? Okay. Anyway, suppose S equals 1, 2, and so on. So S is the set of natural numbers. And the statistical model is P theta, where theta equals 1, 2. So you only have two competing models here. Two competing distributions. This is a model, right? This is a model in which it contains two competing distributions. Right? Indeed, the interesting part is the philosophy, not the bit of calculus that will be used. But the thing is, I mean, let's ask ourselves, how much time in university lecture do you spend on plugging formulas, and how much time do you spend on debating the foundations, right? Anyway, where P1 is the uniform distribution on the integers. Okay, P1 is the uniform distribution on the integers 1 all the way to 10 to the 3. Okay, so even though, you see, even though the sample space S I suppose is a sample space, huh? It didn't say. Where's big S? It didn't say big S. Okay, later we'll see. Okay, so what I worried about is about what it means to say that the probability of hypothesis A explain. Yeah, what it means, right? Is what it even means to say the probability of hypothesis A explain the data versus the probability hypothesis B. It's not clear probability even more than abstraction, right? So the nature of probability was also very muddy. In the early part of the 20th century. So Kolmogorov axiomatized probability in a way that is completely independent of its interpretation. It's just a size. It's just a measure, right? So this way, both the frequentist and the Bayesian can at least use the same mathematical machinery without being bogged down into the discussion, okay, what probability even means, right? Anyway, so here, S is the set of natural numbers. P1 is the uniform distribution on the integers 1 to 10 to the 3. So let's remark on what this means. Uniform distribution on 1, 2, all the way to say big K. Okay, big K is a natural number that's fixed. Means that big X equals little x is 1 over big K if X belongs to the set 1, 2, all the way to big K. And otherwise, Px of little x is 0. And we call the set 1, 2, all the way to big K the support. The support of the uniform distribution. This is called the support. So basically, a support for a probability distribution refers to the set on which the probability mass function or probability density function for the continuous case is non-zero. Okay, that's the support. So here we have in the P1 the support is 1 all the way to 10 to the 3, and P2 is a uniform distribution on 1 to all the way to 10 to the 6. So it's a different support. Further, we suppose that we observe S equals 10. S equals 10. So 10 is both in the first support and in the second support. So assuming that P1 is the true distribution, then S has a probability of 1 over 10 to the 3 to occur. And therefore, by definition, the likelihood function, let's recall the meaning of this notation. What does L1 given 10 means? Given 10 means S is 10. The data is 10. The primary variable 1, the primary variable which equals 1, is the parameter value L of 1. So this is talking about the relative, not relative, but a ranking, a number that we use as a ranking for theta equals 1. It's just 1 over 10 to the 3. And L2 given 10 is 1 over 10 to the 6. Okay, so obviously L1 is bigger. Both values are quite small. But well, the first one, L1 is what? L1 is 10 to the 3, 1,000 times higher. L1 is 1,000 times L2. So as a result, if we use the likelihood principle, we choose theta equals 1 as the true parameter over theta equals 2. So accordingly, we are only interested in likelihood ratios. So this is a likelihood ratio of two competing values, theta 1, theta 2. We're only interested in likelihood ratios for theta 1, theta 2 in omega when it comes to determining inferences for theta based on the likelihood function. This implies that any function that is a positive multiple of L dot S can serve equally well as a likelihood function. Right, so if you multiply the likelihood function by a constant value C, the relative ranking is not affected, so it does not really matter. Somebody asked, Fast Track asked, is L of 1 given 10 equals 1 over 10 to the 0 given, as someone calculated already? Yes, it's calculated from here. It's calculated from this formula here. Sorry, I did not stop to make that connection, but basically this is calculated. When you presume the true value is 1, this means P1 is the true distribution. P1 is the uniform distribution over the set 1 to 10 to the third. So according to the definition of uniform distribution on the set 1 to all the way to k, basically a finite set with k elements. Right? The probability is 1 over k. I was saying because S belongs to this support, S is a value. S is a value in 1 all the way to 10 to the third. So if theta equals 1 is the true parameter, then the data S equals 10 has a probability of 1 over 10 to the 3 to occur. Yeah, that's the consequence of the uniform distribution model, exactly. And the same logic works for the second value. If theta equals 2 is the true value, then 10 being a member of 1 all the way to 10 to the 6 will have a probability of 1 over 10 to the 6. Once again, uniform distribution model. So we can clearly see the likelihood function is determined by both the model and the data. If you change the model, the value of L changes. Of course, if you change the data, the value of L changes as well. Okay, so this is a very simple example. Accordingly, yeah, we were talking about only interested in likelihood ratios. So this is a ranking. L is a ranking. It's like if you guys have seen some economics, the utility function of a consumer is kind of like the likelihood function in mathematical statistics. Like consumers don't literally count euros when we make a decision. Right? Let's say you only have 2 things to buy. You can only buy 2 things, pizza and cookies. Let's say you can only do that. What economists do in their theorization is that they define a function called the likelihood function. Not the likelihood, my goodness, the utility function. The utility function is a function of the consumption bundle. A consumption bundle consists of different goods, like pizza and cookies. Of course, the utility function on its own is pretty meaningless. But it does introduce a ranking. The ranking is real. The ranking is consumers do exhibit preferences of one bundle over the other. Right? So here, what we're doing here, the likelihood function itself, the values of itself is rather meaningless. Instead, what matters is by imposing this ranking system, we can talk about the preferability of parameters, according to the likelihood principle, of course. So according to the likelihood principle, 1 is more preferable than 2. Right? So economists use the utility function to discuss preference of consumers. Likelihood function uses the likelihood function to discuss the preference of parameters of researchers, right? Of empirical researchers. And that's just one way we assign preferences. Anyway, here hopefully we spend enough time on this very fundamental entity here. Okay, so more example. We call two likelihoods equivalent if they are proportional in this way. In general, we refer to any positive multiple of L a likelihood function. Nice. Or you can add a constant. It doesn't matter anyway, right? So in fact, any monotone function, any strictly monotone function of L would be considered a likelihood function. Example 6.12. Suppose that a coin is tossed n equals 10 times and have s equals 4 heads being observed. With no knowledge whatsoever concerning the probability of getting a head on a single toss, the appropriate statistical model for the data is the binomial tan theta model, with theta in big omega ranges from 0 to 1. Okay, so something needs to be mentioned here. In order to use the binomial model, we are assuming the outcome of individual coin tosses are independent. That's a big assumption in the binomial model. Of course, that can be assumed reasonably in practice. Okay. You're tossing coins one at a time, and the outcomes are independent to each other, in which case the total number of heads indeed follows a binomial distribution, which is baked into the assumption of binomial distribution. And also, theta belongs to the set 0 to 1 closed interval. And this is something interesting. So we're including the boundary values 0 and 1. Other authors often write theta equals theta belongs to the open interval 0 to 1 without including the boundaries. Okay, so there's advantage and disadvantage for that, because let's say if you toss 10 times and you get super lucky or super unlucky, and you get 0 tosses and 10, you get 0 head or 10 heads. It is theoretically possible to get such result. But in those cases, you will obtain an estimate of either 0 and 1, which will not be in the parameter set, right? That's awkward, right? That's awkward because we want our estimate to be in the parameter space. Right? So you want your estimate to be always in the parameter space. But this, including the endpoint, also introduces its own inconvenient part. Okay, because as we shall see later on, we would like to differentiate maximum likelihood. Sorry, we would like to. That's how frequentism rolls exactly. So if you include the boundary point, it will include all the possible values that can be obtained from experimentation. So that's a nice thing. But from a mathematical standpoint, this is awkward, because as we shall see later on, we would like to solve optimization problems over the likelihood function, right? We would like to do things like taking derivatives. Right? We don't like to do calculus over the likelihood function, or most commonly, the log likelihood function. So think about if you take log of L, what happened? If you take log of L, it will be the log of 10 over 10 choose 4 is a constant, plus 4 times the log of theta, plus 6 times the log of 1 minus theta. So in that case, theta equals 0 and 1 are not meaningful input. And also, if you do differentiation, you just, in general, dislike a closed set in general. Recall what it means to take derivatives in a multivariable sense in calculus. Right. So let's say if you have a multivariable function, here theta is only a single variable function. Here theta is only a single real variable, but quite often you have a parameter that is vector. And to do differentiation, you want a no open neighborhood. Only an open set has that property. Because if you can include boundary, then a boundary point will not have an open ball that is completely contained in the set. So that's why in subjects like topologies and differential geometry, you work with open set. If you open a textbook on, say, manifold theory, the first definition, say, the manifold, charts and atlas and all of that, right? You want open set to do differentiation. So here there's a little bit of a choice you make here. Right? You can take omega to be the closed interval 0 to 1, or you can take the omega to be open interval 0 to 1. Right? Both have their own difficulties. Okay, so here, but before taking the log, this function is well defined for even the boundary values, 0 and 1. Okay, and we can plot it. You can easily plot this function. It's just a polynomial. So here it says the likelihood peaks at 0.4 and takes the value L equals 0.25088 there. And let's calculate that. Let's verify that, okay? So it's clear that if, suppose, theta is between 0 and 1 in the open interval, and write little l, which is defined as the natural log of big L, which is what we had here, constant plus 4 times the natural log of theta plus 6 times the natural log of 1 minus theta. Let's differentiate. L prime, or dl d theta, is 4 over theta minus 6 over 1 minus theta. Let's set that to be 0. And 4 over theta equals 6 over 1 minus theta. You can solve that. Just the Fermat's condition, the Fermat's theorem, the first order condition in calculus. You give 4 minus 4 theta equals 6 theta. So of course 4 equals 10 theta, and theta equals 0.4. So that's the critical value. And from calculus we know a continuous function over a closed interval can only achieve extremum at two kinds of location. First, a critical point in the interior, and also the boundary point. So here we have 3 possibilities. L is a continuous function over the closed interval 0 to 1. Its maximum can only theoretically occur at the 2 endpoints 0 and 1, or the critical value of 0.4. Of course, we can by inspection tell that L equals 0 at both endpoints. If theta equals 0 or theta equals 1, L is immediately 0. And theta equals 4 gives a non-zero value, and that's positive. So 0.4 has to be the maximum. The monotonicity of the log function is critical. The log function is monotone, but little l is not monotone, right? You mean the differentiability? No, L is not a monotone function. So log of theta is monotone, log of 1 minus theta is monotone, but this linear combination of them is non-monotone. Right? It's just, I mean, this is a simple first-year calculus problem, right? So what we just did is to justify that 0.4 is indeed the maximum. This is always relatively easier to do in 1D. Justifying a maximum exists in multidimensional. No, that the critical points will be the same. What do you mean? It will be the same with what? You mean the if we use open interval, the critical point will be the same. I mean, critical points, we're only interested in critical point in the interior anyway. When we discuss critical points, we always mean a point in the interior. Okay, critical points in the interior or in the open set. Okay, so hang on. Let me just I'll risk the channel being demonetized to show you a source for that method. Okay. Hang on. I'll just a little detail in Calculus by Stewart. Yes, Christian, you're absolutely right. Yeah, sorry, I misunderstood you. You're talking about the monotonicity of log by saying that the maximizing little l and maximizing the big log of l are the same. Yes, you're completely right. Okay, my apologies for misunderstanding. Okay, so for that, I don't need to pull out the Stewart anymore. So basically, that's the little l function. Don't risk the channel, professor. No, I'm not the, okay, I'm not a professor. Thank you very much. Anyway, so here we have the little, big L. This is not little l. If we plot little l though, what would little l look like? Well, little l would have two vertical asymptotes at 0 and 1. And because big L is a probability, right? Big L in a discrete model is a probability. So it is always less than or equal to 1. It's always less than or equal to 1, and it follows that the log of L is less than or equal to 0. And here, in fact, it is strictly less than 0. So log little l looks like this. Little l looks like this. So, and for that, as we mentioned, little l tends to be always negative. Okay, it doesn't always have to be, because for continuous model where big L is defined as a probability density function itself is not a probability. You're our professor. Thank you. Thank you very much. Once again, I would like to reiterate, I consider the viewers of this channel my peers. Okay. Perhaps you can consider me as a leader of the seminar, but there's no hierarchy here. Okay. And I never meant to have my words only passively accepted. Okay. Anyway, so here little l. This behavior of little l is very common. It's basically, it has vertical asymptotes near the boundary, and it concaves down. Okay. And its values being strictly negative due to L being strictly less than 1. However, as I was saying, if L is the likelihood function of a continuous model uses probability density function, and probability density functions aren't necessarily probability. In fact, they're not. Right? Probability density functions are not probability. It's probability over a small interval divided by the length of that interval. So the value of the density can very much be greater than 1. So in that case, little l can have positive value, because L can be greater than 1, little l can be greater than 0. Okay. Okay, so this is important. Let's try to let's put that down in our note. Likelihood principle. There is a range of approaches to obtaining inferences via the likelihood function. At one extreme is the likelihood principle. Yeah, some books use a minus sign to the log likelihood. So in that case, you would minimize the log likelihood because well, it's just a personal taste. Sometimes you hate dealing with negative numbers all the time, so you put a negative sign. This way, the function you minimize is a convex function. Okay. Perhaps it's easier to use results on convexity, such as the Jensen's inequality, if you have a convex function. But at the end of the day, there's nothing substantially different here. Okay. Okay. I was just drinking water. Here, likelihood principle. Notice the careful wording here. This is very interesting. There is a range of approaches to obtain inferences via the likelihood function. At one extreme is the likelihood principle. So, likelihood function turns out, I mean, this wording strongly suggests there are other principles, right? This is just one principle. Not every principle that makes use of the likelihood function is a likelihood principle. So this is another conceptual subtlety here. Likelihood principle. Let's spell that out. Likelihood principle, what does it say? It says if two model and data combinations yield equivalent likelihood functions, then inferences about the unknown parameter must be the same. Okay, so if it means, in short, same likelihood function, same inference. Okay, so that's one. So that's one principle stated outright. In a way, this is an attempt to reduce dimensionality, right? Because the model is a high-dimensional object. The model is, as we remember, the model is a family of probability distributions. And the data typically is a set of numbers. So these are intrinsically high-dimensional objects. We're reducing such great complexities into one object, just a likelihood function. If you have two likelihood functions that are identical, then inferences from those two functions are the same. Okay. This principle dictates that everything we want to say about the unknown value of theta, it must be based on L. So this is so this is one extreme example. One extreme. Most statisticians do not think this way. Okay, just to, for example, give a counter, not a counter example, but in situations where clearly likelihood principle is not followed. Sometimes we wish to penalize complex numbers, or not complex numbers, complex models. This is something called regularization. Regularization. Something called regularization, which is very useful, highly valued in statistics and machine learning. So sometimes you wish to estimate theta, not just purely based on L, but some additional consideration. For example, you wish to penalize theta that are too extreme. Sometimes you wish to penalize models that are too complex. Okay, so in which case you would use something called an information criteria. information criteria. Information criteria will take the likelihood function into account, but with some other characteristics such as the model complexity, as I was talking about. More information criteria. Most commonly, you have AIC and BIC. So these are information criteria and also regularization methods such as ridge regression. I think I briefly talked about ridge regression in yesterday's linear algebra stream. Ridge regression. So once again, that's another example of inference not purely based on likelihood. So this is an extreme principle. But for now, such an extreme principle is good for building intuitions. Before we worry about the more, should I say, more subjective, quote unquote, aspect of what do we consider how do we consider a model to be too complex, right? Yeah, it comes down to bias variance trade-off, avoid overfitting. Yeah. Christian, one little correction though. I mean, I want to say correction, but one little tip is that the bias variance trade-off is an obsolete term. Okay, by modern standards, is not an actual trade-off, because if you say it's a trade-off, it's like an ironclad law. Okay, to have A, you must give up B. Right? That's not really the case nowadays. It is possible to achieve both low bias and low variance. Okay, but still, there's a relation among them. Mathematically speaking, there's a relation between bias, variance, and MSE. Right. Right. So, if you're if you specify the form of a model to be certain class, okay, sometimes you do have this trade-off. Okay, so the trade-off between bias and variance, indeed. But in general, bias and variance, they have a relationship, but it is not necessary that they have to be work against each other. So, no, not trying to be critical in any way. Okay, just in case somebody is reading the chat, and they have perhaps from the wording they may get this rather narrow intuition that there's necessarily a bias variance trade-off. Okay. Doesn't have to be. Yeah, it's more of a tradition, exactly. So here, suppose a coin is tossed in independent tosses until 4 heads are obtained, and the number of trails observed until the 4th head is s equals 6. Then S is distributed negative binomial. Okay, by the way, this is a good review on basic probability theory. How do negative binomial distribution occur? Well, let's first consider a special case of negative binomial, namely the geometric distribution. Uniform prior. Oh, you see, here we have a Bayesian. Uniform prior, or Jeffreys prior, the uninformed prior. Good username. The most famous plot showing variance going down while the bias variance increase vice versa. Yeah, you see you have something like this, right? Uniform prior is talking about a diagram that is common in machine learning. The x-axis is quote-unquote complexity. Of course, that's not a mathematical definition. But then you have the vertical axis. You have 3 plots. Okay, so this is you have the high complexity gives you higher biases, typically speaking, and high complexity gives you lower variance. And the MSE is the sum of variance and variance. Bias and variance, and there's a sweet spot here. Right. So yeah, uniform priors. I assume you're talking about this diagram or something similar to that. Okay, so here we're let's look at example 6.1.3. I was talking about the underlying assumption that gives rise to the negative binomial distribution. This is the basic topic in probability. So let's first consider a scenario that gives rise to the so-called geometric distribution. So in geometric distribution, you would perform independent Bernoulli trials. By Bernoulli trial, we mean an experiment whose outcome is either is binary, basically 0 and 1. Okay, so you're performing independent Bernoulli trials with the same probability of obtain a so-called success. Sometimes we label the success as 1. You do so until you reach a first success. Right? You reach a first success and the experiment just stops. Okay, so that's the geometric distribution. Oh, by the way, I haven't finished the sentence. I was talking about the quantity of interest is the time you need, the time of trials you need to obtain that one success. And that random variable is said to follow a geometric distribution. But sometimes in some textbooks, we also say the number of failures follows a geometric distribution. Because these are equivalent descriptions, but their functional form look a little bit different. So if you're only interested in the number of failures, then the minimum number of failures is 0. Right? You're very lucky you just get the success at the first trial, and the game just stops. Okay, then the experiment just stops. So in that case, you have a 0 number of failure, have no failure whatsoever. But in that case, you would still perform one experiment. So if you count the number of experiments needed to get one success, the support for the geometric distribution will start from 1, 1, 2, 3, and so on. But if you only count the number of failures needed to get one success, the support starts from 0, 0, 1, 2, and so on. Right? So it's really important to look at which convention a textbook chooses to use, because such things can be ambiguous. And also when you when you call functions in software packages, check out what convention they use. Another annoying example is the exponential distribution. So some book uses the rate parameterization of exponential distribution. Some books uses the mean parameterization of exponential distribution. Always check some simple cases to figure out which parameterization it uses. Okay, so here, coming back to the negative binomial distribution, instead of getting one success, you're getting 4 successes. Negative binomial is on page 40. Exactly. Thank you very much. Thank you very much. I appreciate it. Ezra, it's great that you went back to the probability part and look up for the definition. You know what? Let's do that. Okay, because I don't want to assume what definition is being used, what convention is being used, even though the definitions should be quite standard. The conventions are, on the other hand, is not. Okay, let's go to page 44 or page 58 in the PDF as Ezra just mentioned. Thank you so much, Ezra. Okay, so here, negative binomial distribution, let's see what convention is being used. And I assume the author is consistent in the probability and statistic part of the same work. Okay? You assume that, but you never know. Got to be careful. Okay, so here we have 58 here. Oh, hang on. Sorry, 54. My goodness, 58 in the PDF. Okay, there you go. Negative binomial distribution. So here, so you see, k starts from 0. That's the number of failures. So what do we want? Consider again repeatedly flipping a coin that has a probability theta of coming up head and probability of 1 minus theta of coming up tails. Right? Yes, you're right. You don't be sorry. Like I got confused. It's okay. Let r be a positive integer and let y be the number of tails that appear before the r heads. Right? So if we consider getting a head to be the success, the negative binomial distribution as is defined here counts the number of failures. The random variable counts the number of failures. Right? So the support starts from 0. Either there are 2 failures in the example, No, we don't know the number of failures. The number of failures, aka the number of tails, is a random variable. Okay, so yeah, you want R heads consecutively. So imagine the sample path looks like this. So you want R head, right? So you toss, you get tail, 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 and you get head. Oh, that's the first head. And you get head, tail, head, tail, 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 head. Okay. Remember, in the statistic part, we wanted 4 heads. So the sample path of such experiment always end with a head. That's just the last success. You would not perform any more experiment after that. So this is just the last success. From our data, I didn't know. Like I wasn't okay. I wasn't. I don't remember the data there. Okay, but yeah, thank you very much. We'll come back to that. Okay, I'm just here explaining the negative binomial distribution. Can we understand this formula straight from the definition? You don't need to memorize this. You don't need to memorize this at all. Okay, so what does this mean? Well, PYK, that's the probability of y equals k, because y is discrete distribution. So its probability function is just the probability of the discrete random variable equals to a particular value, say k. So here in this sequence, let's say we have k failures. Right? Let's say we have k failures. And R, the number of desired successes, is given. So you set out your goal right from the start that you want R successes. And we just mentioned the last one. The last outcome has to be a success. So in total, we have R successes, and K failures. R is something that is set out even before the experiment begins, and K is just a parameter in the function, the argument in the function. So because the last one has to be a success, how many trials do we have? First of all, how many trials do we have in total? We have R plus K trials. We have R plus K trials, and so therefore you have R plus K minus 1 trials before the last success. And how many trials among those R plus K minus 1 trials are successes? How many? Well, R minus 1. So that's why you choose, you do a binomial coefficient R minus 1 plus K, choose R minus 1. This is choosing R minus 1 successes out of the outcomes that are before the last outcome, because the last outcome must be a success. And then you multiply that by theta to the R minus 1. Those are the probability of successes over 1 trajectories. Okay, so the combinatorics, the binomial coefficient, count the number of possible trajectories, and for each such trajectories, the probability of obtaining R minus 1 successes is theta to the R minus 1, and the probability of obtaining K failures is 1 minus theta to the K, and the last theta is the last success. Okay, so the binomial coefficient counts the number of possible trajectories that satisfies our criteria, and they all have the same probability. Okay, so that's the negative binomial distribution. Okay, so here what do we want? By the way, negative binomial distribution has 2 parameters. It has 2 parameters in general. You have R and K, R and theta. So negative binomial distribution, generally speaking, has 2 parameters. However, in estimation problems, it is usually the case that only theta is unknown. The number of successes desired is not something you estimate. Of course, I'm sure there are scenarios where you do have to estimate such things, which can make things difficult. because R appears in the binomial coefficient, and you cannot differentiate this easily. Okay, you have perhaps use a different method like the method of moment to figure that out. If you do need to verify, if you do need to estimate things like R. Okay, going back to our main subject, likelihood estimation. What do we have? We were talking about the negative binomial model. I mistook A. Oh, okay, no worries. Thanks very much for paying close attention. All right. So here, the hell? Yeah. Where's the negative binomial? Yeah. So here we have S equals 6. S equals 6, that's the number of tails. So that's, yeah, so it's not the total number of experiment. The number of tails is like, that's the number of failures. That's the number of failures. So in total, you have 10 trials to get those 4 heads. And this is just a formula for negative binomial. Oh, hi, Johnny. So you can use the same principle. So here we have a different model. This is a negative binomial. But as you can see, it only differs from the previous example by a constant, by a multiplicative constant. You see, 10 choose 4 is a constant in the previous example, and 9 choose 4 is also a constant in the previous example. The variable part of the two functions are the same. So as you can see, even though the data is different, and the models are different too. In the previous example, we have the binomial model, and here we have the negative binomial model. In the previous example, the data is what? The data is the number of heads recorded. And here, what we're observing as the data refers to the number of tails. And also in example 6.1.3, the sample path, even though it's not visible from the data, is structurally different from example 6.1.2. The difference is in the support. Yeah, so for binomial distribution, the support for the data is 0 to 10. It's a finite set. The support for the negative binomial distribution is 0 to infinity. That means there's no 0 to infinity, but 0, 1, 2, and so on. It's an infinite set. But what I'm trying to say is the sample path should be structurally different as well. For the negative binomial model, the last observation, the last outcome in the sample path has to be a head. Otherwise, the negative binomial model makes no sense here. Right? You're counting the number of tails needed to get 4 heads. So the last one has to be a head, as we mentioned in the review on negative binomial distribution. In the previous example, there is no such requirement. You just toss 10 times and count the number of heads. We don't know what the last outcome is, right, in advance. Here, if you're using a negative binomial model as the model, negative binomial distribution as a model, you know a priori that your last outcome is a head. So these are a different model and different data. Right? If you use the likelihood principle, because the two likelihood functions are equivalent, the inferences about theta is identical. So the likelihood principle asserts that these two models and data combinations must yield the same inferences about the unknown theta. In effect, the likelihood principle says we must ignore the fact that the data were obtained in different ways. If, however, if we take into account of additional model features that beyond the likelihood function, then it turns out we can derive different inferences for two situations. Right? So, I mean, this is of course very general and vague. We don't know what additional model features are being considered here. So here is just an illustration of the likelihood principle. Even though the models are different and the data is different, because what you choose to measure is different, and simply because of the mathematical fact that the two likelihood functions are multiple of each other, the inferences based on those two models are identical. Okay, that's the likelihood principle. So let's read that again. If two model and data combination yields equivalent likelihood functions, then inference about the unknown parameter must be the same. Okay, so likelihood function itself can hide model characteristics and also what sort of data we're measuring. Because if you evaluate the likelihood function, okay, it is unclear, right? Just simply based on this formula. Just based on this formula, do you know what the data is? You don't know. This is just a function about theta. Is 9 the data? The 6 the data? You don't know. This is only known by reading the context. So likelihood principle essentially, as I was saying, this is like a dimensional reduction, almost a dimensional reduction idea. You hide certain information. Okay, so in particular, assessing a hypothesized value, theta equals theta naught, can be carried out in different ways when the sampling method is taken into account. Many statisticians believe this additional information should be used when deriving inferences. Okay, so even though the likelihood principle is intuitive in mathematical statistics, in practice it is rarely directly applied. Okay, as an example of inference derived from a likelihood function, consider the set of the form C of S such that theta consists of so theta of S is the set of theta such that the likelihood function is greater than a particular threshold for some C. So threshold value C. So basically we can draw a picture and visualize what's happening here. So assume the likelihood function is unimodal. So it only has one local max. It only has one global max. Okay, so let's just assume likelihood function looks this way. So what we're doing is we look at the preimage. We look at the preimage of L theta given S of the set C to infinity. So this is CS in this C of S. Okay, I think it's only fair that you also put the C in the parameter of big C as well. Obviously, it depends on the level of likelihood you're choosing. So this is the likelihood region. So the likelihood region. This likelihood region is the preimage. Is a preimage of the likelihood function of the preimage of a semi-infinite interval 0 to C under the likelihood function. And that's the likelihood region. Now, it contains all those theta values for which the likelihood is at least C, obviously. A likelihood region for some C seems like a sensible set to quote as possibly containing the true value for theta. Right? Exactly. So you can treat C as a tolerance level for your likelihood function. Okay, you say, okay, I only accept values of theta such that the likelihood is at least C. Right. Once again, this highlights the nature of the likelihood function. It's just simply a ranking system. Okay. All right, so you have this threshold C. A likelihood region for some C seems like a sensible set to quote as possibly containing the true value of theta. If theta star, a particular value, a parameter theta star is not in the set CS, then by definition, then by definition, the value of theta, the value of the likelihood at theta star, L theta star given S, is less than L theta given S for every theta in CS. So imagine here, if you have a theta star, the value of theta star, whose L value, whose likelihood value is below C, then theta has to be outside of the set CS. Okay. Just from the definition of CS. So it's not well supported by the observed data. Okay. So this value theta star is cast out by our criteria. The size of CS can then be taken as a measure of how uncertain we are about the true value of theta. Okay, the size. The size is once again is a vague concept. What do you mean by size? Do you mean the length of the interval? Well, we don't know, because theta here is not necessarily a continuum value, right? So it's some sort of measure of CS. So some sort of measure of CS. So it's like it doesn't have to be a probability measure. In fact, we don't have a probability measure. Right? We don't have a probability measure over the parameter space. So the size of CS is once again some sort of measure, but not a probability measure. It can be, for example, the big measure, the length, or it can be the counting measure, if you talk about theta being a discrete set of parameters. Okay, so some sort of measure is needed to discuss the size of CS. Likelihood region, the size of likelihood region. Okay, right. The larger the CS is, obviously means obviously corresponds to more uncertain about theta. So we're left with the problem, however, of choosing a suitable value for C. Right? So here C is an arbitrary value. We don't know what C is. How do you choose the value of C? And as example 6.1.1 seem to indicate, 6.1.1, that's the very first example. Right? You only have two competing theta values, 1 and 2. So you only have two competing distributions. Right? So what does that say? 6.1.1 says, seems to indicate the likelihood itself does not suggest a natural way to do this. It does not suggest a natural way to do this, right? Because the likelihood function, well, it's just a function over two values. Okay. Good catch with a complex form. With a complex form. Good to see you. Are you talking about the? Oh yeah, Leo lectures. Thank you very much. Oh, thank you very much for joining the stream. By the way, Christian sent the link of your stream to my Discord server, which you are very welcome to join. And for that reason, I check out your stream. Before, I didn't even know your channel existed. So thank you, Christian, once again. And thank you, Leo, for hosting the stream. Yeah. So here, I was talking about the size of CS requires a notional measure. This requires a notional measure on the parameter space. So once again, you see, I was talking about the lack of probability measure over the parameter space in the frequentist diagram. I was talking about the lack of probability measure in the frequentist diagram, but it turns out you would have to introduce some sort of measure anyway, just to discuss uncertainty about a certain parameter, right? For example, the most common one being the length of a confidence interval. Right? In practical statistics, a wider confidence interval indicates a greater uncertainty. Right? So just gonna head down now. Yeah, for sure, no worries. Thanks for dropping by anyway. So far, oh, by the way, here, the likelihood function itself does not suggest a natural way to do this. In section 6.32, we will discuss a method for choosing C that is based on additional model properties beyond the likelihood function. Okay, we'll be looking forward towards that. I don't think we'll have time to cover that because we started the statistics stream officially at A30 also, because I mean I usually spend about 20 or 30 minutes discussing the overall objective and sometimes philosophical principles and the stance of the of myself in the first 30 minutes before I dive into the math. So I think I'll do another 30 minutes on statistics and then we'll transition to ballistics. Highly recommend, dude. I've seen pop up everywhere. Oh, what pop up? Um, Hi Z Phi. Yeah. Um, yeah. So here we were talking about the choice of C being unclear here. So this is something we need to pay attention when we study later part of the chapter. Okay. So likelihood region. Likelihood region is simply you select a minimum tolerable level of likelihood. Um, okay. Yeah. Great. So here we have a problem of selecting C, which will be later answered. So far in this section, we have assumed that our statistical model are comprised of discrete distributions. Yes, the definition of likelihood is quite natural, as L theta given S is simply the probability of S occurring when theta is the true value. This interpretation is clearly not directly available, however, when we have a continuous model. Right? Because for continuous model, the probability of obtaining one particular data point S is 0. Imagine, however, that f theta 1 of S is greater than f theta 2 of S. That S is R1. Okay, once again, assuming the data point is just one number. Assuming the continuity of all the density functions. Assume every density function is continuous. Okay, then you would have this particular feature here. So we know that the density function measures density function is a ratio between the probability. Imagine, okay, I don't know how to draw this, but basically, okay, this is S. Let's draw a small interval, quote unquote, small interval around S, A, B. Right. So the probability of big S belong to A and B is, roughly speaking, the density function f theta of little s times the interval length b minus a, assuming that b minus a is small. Okay, so assuming that the continuity of every theta near s, every theta at s or near s, we have the probability of theta 1, the probability measure of v. Okay, the probability measure of v, supposing that theta 1 is the true parameter, it will be an integral. It will be an integral which will be greater than p theta 2 of v, which is the integral from a to b f theta 2 of s. Okay, so containing for every interval v a to b containing s that is small enough. So this is a direct analogy to the discrete case. In the discrete case, it's simple. You simply have the probability of observing S being greater or smaller. You can directly compare that here, but in the continuous case, because density aren't probabilities themselves, right, instead you have to discuss the probability of obtaining samples that are near to the observed values. Okay. So we interpret this to mean that the probability of S occurring when theta is true is greater than the probability of S when theta 2 is true, even though this sentence is not literally the same. This sentence is not literally true, because under continuous model, the probability of S occurring, so this quantity is precisely 0. Okay? If we were to interpret things literally, this will be 0. So this is understood in a neighborhood sense. So theta S supports theta 1 more than theta 2. A similar interpretation applies when S is a vector value and V is a region, is a region in the n-dimensional subspace. Not a subspace, but n-dimensional Euclidean space. Okay. So yeah, so that's the likelihood principle can also be applied. Same likelihood principle can also be applied to continuous model as well. Okay. But now it's just the likelihood function is defined numerically speaking as the density function instead of the probability mass function. Once again, the interpretation of the inputs are the same. Okay, theta is the primary variable, whereas s is secondary or straight up treated as constant. Okay. Here, therefore, in the continuous case, we again define the likelihood function by L of theta given s equals to f theta of s, and interpret the ordering this imposes. Right, the ordering this imposes. Interpret the ordering this imposes of the value of theta exactly as we do in the discrete case. Once again, the role of the likelihood function is simply a ranking system. This is a ranking system, regardless of the underlying distribution is continuous or discrete. Okay. Now again, two likelihoods will be considered equivalent if one is a positive multiple of another. Great. Now consider a very important example. Okay, we'll have to do some actual math for this example. Suppose that theta 1 all the way to theta n is an observed independently and identically distributed ID sample from normal distribution with zero mean and theta and sigma 0 square distribution. What do I mean by that? The logic of discrete and continuous makes sense, but for Euclidean space in n dimensions, well, here S is a sample point, is a sample data point. S in Rn just means that it has n components. It does not necessarily say those components take discrete or continuous values. Okay, I mean the whole distinction between discrete and continuous distribution is a matter of practicality. Okay, it's not mathematically important. And mathematically speaking, the distinction between continuous and discrete distributions is kind of arbitrary. It's kind of arbitrary. We mean in practice, most distributions you occur either take values over a discrete set or a continuum. So it's convenient to discuss those things. But fundamentally speaking, there are mathematical properties, things like, for example, the nature of the expectation, for example, does not bear that distinction at all. It is largely an artificial distinction meant for practical purposes only. Okay. In general, a distribution can be neither discrete or continuous. Anyway, here, going back to the normal model, we assume that the mean is unknown, theta is unknown, but the variance is known. Okay, so as a result, the likelihood function, which is just numerically the same as the joint density function. And because of the ID assumption, the joint density function is simply a product of individual marginal density. So that's why ID is so widely used, because of the relatively easy way you can express the joint density. Okay. So now you just plug in the formula for the normal density. Plug in the formula for normal density, and then you do the algebras, which we will do shortly. Okay, let's do this in our notes. Example 6.1.4. So you have x1 all the way to xn, follow normal distribution with theta as this mean, unknown mean, and sigma 0 squared being this known variance. Okay. Okay, so the likelihood function numerically equals the joint density. Numerically equals the joint density, which by ID assumption is the product. is the product of the f theta xi, and then use the normal distribution assumption. This is the product of the density. Actually, you know what? Let's put it underneath. So basically, this is what we have. 1 over square root of 2 pi sigma 0 exponential of negative xi minus theta squared over 2 sigma naught squared. Okay, so that's the likelihood function. Let's try to simplify this a little bit. So first you have, well, here, because theta naught is, or not theta naught, but sigma naught is a constant. So you simply get 2 pi raised to the minus n over 2 times theta naught to the minus n. And then by the law of exponents, you get just exponential to the negative summation I from 1 to n. xi minus theta squared over 2 sigma naught squared. Okay. Once again, remember this is a function in theta, so it might be useful to figure out the exact dependency on theta. This seems to be a quadratic function. Right? Let's just isolate the key feature here. So just look at the part that actually depends on theta, because 1 over 2 sigma naught squared is another constant, so we can just ignore that. Note this is a quadratic function in theta. It's a quadratic function in theta, and actually let's do this manipulation here. Okay, so it might seem rather random, but once again, if you've seen a lot of videos on this channel, this is not random at all. Okay, this has to do with orthogonal decomposition. Okay, so I'm trying to do is I'm going to isolate, sorry, not isolate, but subtract n plus x bar, where x bar is the arithmetic mean of the sample. Okay, you see, okay, what the hell am I doing? Why do I do this? Well, this is because in an n-dimensional space, 1, 2, all the way to n. Okay. A data point x1 to xn is a vector. Oh, thank you for joining the membership, man. Thank you so much. Welcome to uniform. Welcome to uniform. Okay, what the hell is that? Well, it has to. It's a sort of an inside joke, because in real analysis, uniform convergence and L2 convergence are quite common. Uniform convergence is more restrictive. Okay, so L2 is it also stands for level 2, basically. Okay. Okay. Thank you very much for joining the membership. So here, I'm saying is the vector x1 all the way to xn projecting onto the line span of 1, span of the vector 1, 1, and so on, with components all 1 is what? The projection is x bar times 1. So what we're really doing here, this is the vector the norm of a square norm of a vector, x vector minus 1 x bar plus 1 x bar minus theta. Okay, remember x bar is a constant, has nothing to do with I. Theta is also a constant, has nothing to do with I. So these two vectors are orthogonal, as is shown from the picture. x minus 1 x bar is this part, is perpendicular to 1. So these two are orthogonal, so by the Pythagorean theorem, you get x bar minus, not x bar, but x vector minus 1 x bar length squared plus 1 x bar minus theta length squared. Okay, so that's just the orthogonal decomposition of this derivation. So basically here, the first is what? The first is the summation of xi minus x bar squared, I from 1 to n. And then plus, well, the second vector has identical components. Each component of the second vector is x bar minus theta. So it's just x bar minus theta squared times n. Why times n? Because the vector 1 has components of all 1. Right? So the sum of squares of them is just n. So therefore we summarize this identity. This identity is nothing but a Pythagorean theorem. Okay. So we wish to inject geometry into statistics, or geometric essence in statistics whenever possible. So you can see here, the immediate consequence is that the minimum is what? The minimum is this. This is greater or equal to the sum of I equals 1 to n, xi minus x bar squared, and attains equality when theta equals x bar. And theta equals x bar. So let's go back to this likelihood function. Likelihood function L theta given x1 all the way to xn. So it's this thing. You have the constant at the front. It does not matter. So let's just ignore the constant. Ignore the constant, and you get just the exponential. Let's just write, okay, constant times the exponential of this thing. So you get 1 over 2 sigma squared, 2 sigma naught squared, times what? Times the sum I from 1 to n, xi minus x bar squared. And this is a minimum MSE basically. And then you minus what? Oh yeah, n over 2 sigma naught squared, 2 sigma naught squared, and then x bar minus theta squared. That's the likelihood function for this model. Okay. Yeah. So let's get back to the text and see how we did. Okay. Likelihood function for the ID normal model. You see, so here what we did is, yeah, you see it's completely equivalent. S squared, in the textbook, S squared is the sample variance. S squared is 1 over n, 1 over n minus 1, 1 over n minus 1, sum of xi minus x bar squared, I from 1 to n. So why divide by n minus 1? Well, it's clear from the picture. You have an n-dimensional space, and you're projecting onto the span of 1, which is a one-dimensional space. The orthogonal complement has dimension n minus 1. So this means the residual vector here, the residual vector lives in a subspace of dimension n minus 1, and that's the so-called degrees of freedom. So that's the so-called degrees of freedom. The degrees of freedom, fundamentally speaking, in statistics is a geometric notion. It is a concept that is borrowed from classical mechanics. So you often see degrees of freedom arises in different contexts. And here we say that the degrees of freedom of the residual vector is n minus 1, because the residual is obtained by projecting onto a one-dimensional space. But let's say if you're solving a linear regression problem and a simple linear regression problem, then the orthogonal projection is onto a two-dimensional space, in which case the residual will have a degree of freedom of n minus 2, not n minus 1, because now the orthogonal complement has a dimension of n minus 2. And a similar interpretation, like geometric interpretations, can be said about things like the degrees of freedom of chi-square distribution, t distribution, and f distribution. Degrees of freedom is always a geometric notion, some sort of dimensions, okay, of a surface or a plane. Okay. So basically what we have here is that you see you have a constant times exponential of 1 over 2 sigma naught square, sum of I from 1 to n, xi minus x square. See this part, so both are independent of theta. And finally the last part times the exponential of minus n over 2 sigma naught square x bar minus theta squared. So only this last part has to do with theta. So as you can see, as far as getting information about theta is concerned, only x bar matters. Of course, it depends on the sample as a whole, but it depends on the sample only through its mean. Hello, what did I just miss? Well, we were talking about maximum likelihood, or actually, we didn't even talk about maximum likelihood, but just the definition of likelihood inference. How is the likelihood function defined? Its subtleties, its interpretation, and why likelihood is not a probability, the likelihood principle, and here we actually, near the very end of the mathematical statistics stream, we finally did some math of basically calculating the likelihood function of a normal model. Okay. Once again, I hate to bring up the contrast we do compared to, say, a typical university lecture. In a typical university lecture, you would give out the definition of likelihood function and then immediately jump to examples and start calculating stuff. Okay. So yeah, the geometric understanding. Yeah, you can go to the mathematical statistics playlist, by the way. So I hate to repeat myself all the time because this is something that has been already formulated in a video format. Okay, so go to the mathematical statistics playlist of this channel, and you will, for example, if you check out the video on the first video, so actually the second video on it's called geometry is just statistic. Okay. And you'll see the discussion on degrees of freedom there. And also I mentioned in a video called what the t distribution is really about. Once again, the degrees of freedom in t distribution is another dimension, and this time is a dimension of a sphere, okay, instead of a plane. So yeah, degrees of freedom in statistics is always some sort of dimension. A dimension of a plane, dimension of a sphere, dimension of a surface, and so on. Okay. Just like degrees of freedom in classical mechanics. Okay. Okay. It's the yeah. Anyway, I think it might be the third t distribution second. Yeah, exactly. Yeah. Okay, so here we're talking about a notion. An equivalent simpler version of the likelihood function is given by this, which was exactly what we just derived. We notice that there is this part of the likelihood function is independent of theta. So what we mentioned just a few minutes ago, two likelihood functions are considered equivalent if they only differ by a multiplicative constant. So only the part that depends on theta actually matters. Remember, theta is the variable. Everything else is treated as constant. And that constant, which is a function of the sample point, is exactly X bar. So this is actually super interesting. See, this is actually super interesting. So basically, we know the likelihood function depends on two things, as we mentioned. The likelihood function depends on both the model and the data. Right? The fact that it depends on the normal distribution is obvious because we use the normal density. The way it depends on the data is very interesting though. Okay. The way that the L here depends on the data is interesting though, because only X bar plays a role. Okay, not the variance, the sample variance, not anything else. Okay, just X bar plays a role, or equivalently speaking, the sum of Xi plays a role here. So, to summarize, the likelihood function for this model depends on the data only through X bar, or a one-to-one function of X bar. And this is exactly the idea of sufficiency. The idea of sufficiency, or X bar being a sufficient statistics for theta, says all the information regarding the parameter theta contains in X bar only. If let's say two samples have the same values of X bar, then they're indistinguishable as far as inference over theta is concerned. This is an important idea. Okay, and in fact, the idea of sufficient statistics will be a video topic. The idea of sufficient statistics as well as exponential family, perhaps in 2 videos, because these two are intricately linked to each other. Okay, the idea of sufficiency was a powerful principle proposed by Fisher, roughly about the same time that he invented or formulated the maximum likelihood principle. Almost immediately after that, he formulated the idea of sufficiency. But it turns out that the idea of sufficiency, although attractive, it is pretty restrictive. It has to do with the fact that it only works for exponential family. Okay, so it's actually a very deep idea, and the fundamental reason is, once again, it's geometric. It's more specifically linearly algebraic. Okay, so what's an extremely fascinating topic which deserves their own videos. Okay, so here, this is just a glimpse of what we're about to experience I guess, in future streams. The likelihood function here only depends on the data only through X bar. So X bar is a sufficient statistics for this model. Okay. Anyway, here we have a bunch of examples. We put in some specific numbers. Looking forward to that. Yeah, we'll do. I really have to make some statistics videos soon, because a lot of people subscribe to the channel due to my statistics video blow up. Okay, let's just put it this way. I didn't expect that at all, but for some reason, well, the channel got into today's audience, a size of the audience of this size, is because of the heavy lifting done by the statistics video. I should really put out some videos on that. But later on, I mean, the videos on stochastic calculus attracted its own audience. I'll have to balance them. Anyway, so here, the likelihood function peaks at X bar, right? This was obvious from the orthogonal projection identity. The likelihood function, to maximize the likelihood function, is equivalent to minimizing the exponent. How is the minimum of the exponent achieved? The minimum exponent is achieved when the quadratic function in theta equals X bar. So this is actually something very deep here. This is not a fluke. This is not a fluke. So basically, here in this box identity, what we're doing here is we're solving a least square problem. Okay, we're trying to minimize the sum of squares. This is a least square problem. This is a fundamental linear algebraic problem. This problem turns out to be equivalent to maximized likelihood. Okay, the equivalence between least squares and max likelihood is a specific feature of Gaussian. Okay, this is not a fluke. Max likelihood turns out to be equivalent to least square in this example. And that's due to the fact that the distribution is Gaussian. And in fact, it's a defining characteristic of Gaussian. You can actually derive the Gaussian distribution. You can derive the Gaussian distribution from the assumption that max likelihood and least squares are equivalent. How amazing is that? Let me repeat that again. Suppose that the underlying IID distribution to be unknown. Okay, suppose this is something to be determined. But it is known that for this distribution, max likelihood and least square are equivalent. Then the distribution has to be Gaussian. So that's one of the characteristics of Gaussian. It's in one of the videos, by the way. It's the video called Statistics' Biggest Drama and the Origin of Gaussian Distribution. So yeah, so in that video we touched on the controversy surrounding the priority of least square method. Lejeune claimed, of course, Lejeune published it first. Lejeune first published the method of least square, but Gauss claimed that he invented it first, thereby sparking a controversy. However, it is true that even though the priority is disputed, Gauss did contribute significantly more than arguably any mathematician of his era on the method of least squares. For example, he pointed out the connection between the method of least squares and probability theory. Right. So, yeah. So basically, that was the result. This is called Gauss's law of error. So Gauss's law of error says, so suppose that the underlying distribution of the errors has this specific property that max likelihood and least square are equivalent. Then the error distribution has to be Gaussian. Yeah, never mind, it was Lejeune. Yeah, Lejeune and Gauss had a bit of a back and forth over the priority of and it's not just like a small dispute. Okay, it lasts for at least a decade between the two, and their relations are very strained because of it. And in my opinion, Gauss was kind of being mean. He didn't have to. Be mean to a fellow mathematician. Okay. Because he could have easily acknowledged the priority of Lejeune and published his own research on least square, which is also equally, but if not more deep. Okay, Gauss did genuinely made original contributions to the least square. Nobody's denying that. But if you choose to publish your result only after they are beyond criticism, then don't be surprised that others might publish their results first and claim priority. It's just a simple trade-off you have to accept. And the thing is, Gauss don't even need the result to survive academically. He's already an established mathematician, right? It's not like having another theorem or method under his belt named after him would give him tenure. He already had that. Right? He's already Prince of Mathematics in Europe. So it seems rather unnecessary. Right? Ego, man. It's just simply just a matter of ego. Scientists, once again, are not saints. Okay, so even though this calculation here is rather mechanical, right? This calculation is perhaps a little bit tedious and mechanical, but the underlying pattern is actually very deep. Okay. Anyway, let's go back to the main text. And before after finish that, we'll get to we'll finish another example so that this section is finished. Next time we'll go to sufficient statistics. Okay, here, if you plot this function and you set the threshold to be 0.5 like this, and you can easily calculate the cutoff values. So you want your likelihood to be what? You want your likelihood to be at least 0.5. Once again, 0.5 seems like a pretty arbitrary threshold, right? We don't know why it is chosen, but well, let's just put it 0.5. So if, let's say, C is the minimum tolerable likelihood is 0.5, then the value of theta that are permissible ranges from 3.06 all the way to 3.53. Right? So this is called the location normal model. Right? This is called a location normal model. It is impractical for many applications because the variance is assumed to be known. Reno says, I think non-Euclidean geometry was also discovered by Gauss, but is named after other independent discoveries. Exactly. Reno, you're completely right. So once again, going on a side tangent, basically what Vernon is saying is that non-Euclidean geometry is also something independently discovered by Gauss along with a few other people. There's actually another piece of drama surrounding that about Gauss, which I think, even though Gauss made the opposite decision compared to what he did for the least square dispute, they were equally telling about his character. What do I mean by that? So non-Euclidean geometry nowadays is credited to three individuals for its discovery. First is, I think it's called Bolia. My goodness, I probably didn't even spell it right, let alone pronounce it right. It's a Hungarian mathematician. It's a very young one. When he discovered non-Euclidean geometry against his father's wish, because his father told him that this problem is so difficult, spending on it would just be a waste of time. But he did not give up, and in the process discovered non-Euclidean geometry. So Gauss did a lot of actually questionable things throughout his life. His relation with his sons were disastrous due to his just tyrannical patriarchy. Let's just put it this way. So Gauss's relation with his son were very, very poor. So who's that person? My goodness, I can't even remember. So that's the person. Bolyai. Bolyai? Bolyai. Yeah, Hungarian mathematician Bolyai. This is a person, Bolyai. Yeah. So here, so he discovered this. He discovered the non-Euclidean geometry, and along with Bolyai, along with Gauss himself, as well as a Russian mathematician called Lobachevsky. I don't know if that's the way to spell it, but so it's here mentioned along with Lobachevsky. And the particular non-Euclidean geometry that these three discovered is nowadays known as the hyperbolic geometry. And by the way, Lobachevsky, perhaps not so well known in the West, is a household name in Russia. Exactly. Good to have a short name and pronounceable name like Gauss. Okay. So Lobachevsky was perhaps the most famous Russian mathematician in the 19th century, in the early part of the 19th century. So Lobachevsky, unlike Gauss, Gauss himself also discovered non-Euclidean geometry, but he did not publish. So what these three people did regarding the Euclidean geometry, that's their own discovery, by the way, are very interesting. So Lobachevsky discovered and published it and caused a major firestorm, which almost costed him his academic career. Because Euclidean geometry was treated as the absolute truth at the time. Right? Immanuel Kant, the German philosopher Immanuel Kant, wrote his treatise on philosophy, in particular the Critique of Pure Reason, citing Euclidean geometry as its own foundation, So Immanuel Kant has this philosophical system on how human beings can obtain knowledge without quote unquote experience with the world. And Euclidean geometry, according to Kant's understanding and also the prevailing understanding at the time, consists of human beings' understanding of quote unquote space
without the need to perform measurement. Right? So Euclidean geometry at the time was considered the absolute truth, and saying anything contrary to that was a contrarian move. So Lobachevsky did that. You also, of course, know the political fallout of coming out and say he has also discovered non-Euclidean geometry. So Gauss chose to hide that decision. He chose to hide that discovery of him. And Bolyai, the Hungarian mathematician Bolyai, was relatively unknown at the time, but he wrote a letter to Gauss. He wrote a letter to Gauss and asked him to check for the soundness of the theory. Guess what Gauss said? Gauss wrote in reply that to praise this work is to praise myself. You see, what a... So Gauss chose to not support Bolyai. Why? Because he was afraid of angering the establishment at the time. You see, this is a very different decision compared to the least square fiasco he had with Legendre, right? So Gauss also truly discovered the method of least square, but chose not to publish it. And when Legendre chose to publish it, Gauss came out and saying, I discovered this first. Of course, Legendre was very pissed off about it. Right, so why did Gauss came out and compete for the priority of least square? Because least square was so widely accepted. Hang on. So I'm going to finish off this historical digression very soon. So Gauss chose to hide his own discovery and chose not to support Bolyai on non-Euclidean geometry, fearing the wrath of the establishment, while at the same time competed for the priority of least square because of least square was widely accepted. Opposite direction, both motivated by fame. He is a person that is more interested than his own dominance rather than genuine scientific progress. Anyway, let's come back to the question. After reading up the definition of sufficient, I still don't understand how MLE is identical. Can you elaborate just 30 seconds on how sufficient statistic of T, sufficient measure of T equals MLE for Gauss alone? Okay, so yeah, it actually has nothing to do with sufficiency here. I was saying that if you, let me just point to the right video. Hi, Zeph, are you talking about my remarks that maximum likelihood equivalent to, the assumption that maximum likelihood equivalent to least square implies Gaussian? Is that what you're asking about? Or are you doing something about sufficiency? Or asking about something about sufficiency? Which question? So what exactly? Because the question itself seems a little bit ill-phrased, but that's okay. I'm just trying to clarify here. Which one? Which one? Is it has to do with sufficiency or has to do with equivalence between least square and max likelihood for Gaussian? Option 1, sufficiency. Option 2, equivalence between ML and least square. Just type a number. Okay, don't need to spell anything. Okay, if not, if you can't decide, I'll explain. It's about the second. Okay, about the least square. So that's what's the video. Okay, let me go to the video and I'll put it in the chat. Okay. Okay, I'll put it in chat. Okay. Mathematical statistical geometric approach in the playlist. That's the playlist, and I'll give you the right video.
Today we'll talk about perhaps the biggest drama in the...
Okay. Anyway, so that's the video. called Statistics Biggest Drama and the Origin of Normal Distribution. Right here. No, don't be sorry. Yeah, this is highly non-trivial. I mentioned it in passing because I already made a video on it. I don't assume everybody has watched that video. But yeah, that's the explanation. And in particular, the equivalence. Okay, I'll give you the timestamp. So here, okay, actually, the timestamp is 10.51. So 10.51. So if you look at the, actually, you know what? Let's just put it here, okay, on the screen. So this is a statement. Gauss's law of error. Suppose observations x1 all the way to xn are generated by the model, a true parameter theta plus some error. Okay, epsilon I or IID follows the distribution Fe. Okay. By the way, E here is not the Euler's number 2.7. Okay, it's just the argument of F. F is a smooth density function. If for every sample x1 all the way to xn, the max likelihood estimator of theta is the sample mean, then F must be Gaussian with zero mean. And why is this equivalent to least square? Because in the earlier part of the video, we argued that least square is the least square solution. The least square solution is the sample mean. Remember, we did here as well. Okay. The least square solution is the orthogonal projection, which is equivalent to the sample mean. So that combined with this statement tells us the maximum likelihood is equivalent to least square for the Gaussian case. Right. So here we, in our notes here, we assumed Gaussianity. We assumed Gaussianity and showed that maximum likelihood is equivalent to least square. Here in this statement, we're doing the converse. We assume the equivalence between maximum likelihood and least square. We proved that the error distribution has to be Gaussian. This is a characterization of Gaussian. This is a characterization of Gaussian that has nothing to do with central limit theorem. That's why I like it so much. And the proof is actually a differential equation argument. You write down a likelihood function, you differentiate set to 0, and then you just end up analyzing a functional equation. And the functional equation forces the form of Gaussian. Okay, so just briefly going over this. This is a distribution. This is the differential equation. And solving this differential equation, you get integrating, you get the Gaussian. Okay, this is a highly non-trivial result due to the ingenuity of Gauss. Yeah, Gaussianity is a made-up word. Okay, it's perhaps normality is better. Okay. All right, so that's the thing. Okay, so I think we're let's continue. Let's continue maximum likelihood next time. Okay, I'll leave one example for the next time because it serves as a warm-up exercise. Okay. Oh, gotcha. Thank you again. No worries. Glad it helped. Okay. So yeah, I personally find mathematical statistics endlessly fascinating. It's just, for me, there's something so attracting about it. I cannot even point to the exact result that tells me that this is a subject worth studying. Unlike, say, abstract algebra, differential geometry, and whatnot. I think mathematical statistics fascinates me more than any math subject. Okay. Anyway, so this concludes the statistics part of the stream. And by the way, how many people are watching? I'm just interested. I can't see it from my OBS, so I have to go to my phone to find out. 14 people. That's pretty good. That's a kind of a consistent number, isn't it? Because on Saturdays are also 14 people when I in halfway. You're exceptional at conveying that excitement. I watched almost the entire thing. Oh, thank you very much. Ezra, what entire thing? The yesterday's stream? But anyway, thank you guys so much. Doesn't matter. Okay. Now let's go to the ballistics part of the video. So for to those of you who are new to this book, just like to mention that this book, because it's written by mathematicians, not physicists or engineers, used to find statistics boring. Then I became a high school teacher and had to teach it. Nice. So I dive into it, have loved it ever since. Exactly. Yeah. So this video, we started at 8. We started, so it's nearly 2 hours and 48 minutes. Okay. Okay. Yeah, I used to find statistics boring. This is because usually how statistics is presented, right? It's just a bunch of recipes. It's like a cookbook. Well, you plug in the data, it gives you a sample statistics, and then you write a conclusion about it. That's about it. It's very procedural, right? It's great for, well, it's great for writing a piece of software, right? If you provide step-by-step instructions. But unless the underlying intuition is clarified, it does seem like a pretty boring subject, right? Right. So this is just an unfortunate way statistics are usually typically taught. Once again, you may argue that this is due to the fact that statistics is so popular. Statistics is so powerful. It's perhaps a victim of its own success. What I'm trying to say is statistics is so useful in so many diverse fields, right? That even math subjects, that even non-math majors have to take them nowadays. Let's say if you're a social scientist major, if you're a social science major or computer science major, you still have to take statistics, which means you don't always have the necessary foundation to understand the intuition, right? Because to gain a non-trivial understanding, a really conceptual understanding of mathematical statistics or just statistics in general, right, you need to have some knowledge about probability, which is something that is not usually always assumed for all majors. So what you end up doing is a bunch of hand-waving explanations as well as plug-and-chug exercises, which gives this impression that statistics is just a huge collection of formulas to memorize and hurdle through. Right? As I was saying, this is perhaps due to statistics' own success because it's so useful in so many different fields that students have to take it from a wide background. So the prerequisites have to compromise, and then you end up having this perception that statistics is boring. Its history is highly colorful, though, and not just from a mathematical point of view. Its history is very colorful because of the sheer amount of controversy surrounding its foundations. Like, for example, explaining p-value is not a simple matter. Even though p-value is used pretty much in every statistical study ever. Explaining the meaning of p-value is not a simple matter. Okay. So, anyway, let's come back to the ballistic part of the video. So, because of this book is written by mathematicians, its language reflect that. Okay. In a ballistic book, you will in this ballistic book you will see things like definitions, theorems, and whatnot, proofs. And in the first chapter, it laid down the foundation of the subject. It's called Mechanics, Dimension Analysis, and Statistics. Oh, well, I was under the impression that statistics is mostly heuristic and some very convincing logical theory. Its foundations can be heuristics, right? I was saying like, and Christian repeatedly pointed it out, that the maximum likelihood principle is highly heuristic. It's an intuitive principle, but once you choose that principle, you have to do it the mathematical way. Okay, because once you have selected a particular optimization criteria, then the rest is highly rigorous mathematics. Because textbooks have those hand-waving explanations, right? So that's why I chose the Evans book, right? The Evans-Rosenthal book. That's pretty rigorous by introductory book standard. So yeah, if you study that book and do a lot of exercise from it, you will learn a whole lot of stats. And it's completely free, and it has a solution manual. So what else could you ask for? So anyway, here, chapter 1, Chapter 1 laid down the foundation, the mathematical and physical foundation of this discipline, exterior ballistics. And as the author themselves claimed, warned, that the math part is likely to be trivial to mathematicians, and the physics part is likely to be trivial to physicists. So let us tolerate each other's ignorance. Okay, so that's the comment by the author. So as a result, if you can see, the organization of this chapter goes as follows. From 1 to 6, section 1 to section 6 of chapter 1 are about vector and calculus of algebra. Sorry, the algebra and calculus of vectors and vector valued functions. So these are typically calculated. So these are all typically covered. Okay, these are typically covered in linear algebra, vector algebra, or even high school geometry, and perhaps vector calculus and some basic vector calculus. And then we go to section 7, 8. Section 7, rigid motions. Section 8, mass, momentum, and force. Section 9, center of mass. These are obviously physics. And arguably, physics ends with dimensional analysis, even though dimensional analysis is a purely mathematical result. But because of ballistics and fluid mechanics uses so much dimensional analysis, you can consider it a theorem in physics. But dimensional analysis in Buckingham Pi theorem. Okay. One of the most miraculous applications of linear algebra, dimensional analysis and Buckingham Pi theory. And then after section 15, there's some probability and stats. The Stieltjes integral, probability measure, expected values, CDF, variance, normal distribution, independent distribution. Right? These are stats. So this chapter 1 already is a chapter 1 is a highly interdisciplinary. It ranges from vector algebra, classical mechanics, and to probability theory. Okay, so let's last time we went through the definition of vector, but I'm afraid, I suspect that because of the audience of this channel are highly mathematically inclined, right? So perhaps explaining things like addition of vectors would bore them. So why don't we start from section 7, rigid motion? Once again, this is, I'm not skipping them and claiming them to be trivial, but the thing is, it's just a matter of actually reading mathematics and physics textbooks that you don't always start from the very beginning. You don't always start from the very beginning and read from page 1 to page, 852. You don't always do that from cover to cover. That's typically not very practical unless you're taking a formal course. So what we can do is we select a section that we're interested in and see how far we can go until we hit a wall, and then we come back to the previous part. How about that? Oh, so that's the hang on. Let me just reply a message. This is my mom. Okay, I'm telling her I'm having a live stream. All right. So here, let's go to section 7, rigid motion, page 25. So yeah, if you're unused to or horrified by the typesetting, it's because this book was written after World War II. What if they also introduced new characters in the first section of the book and we missed them? Good question. Very good question. Very good question. So if those characteristics are used later, you will hit a wall. If those are introduced and you don't know, you will hit a wall. Okay. If they're introduced purely for the novelty factor, and it's not really used later on, I wouldn't call that a huge loss, right? Right. So that's the thing. Okay. So, um, yeah, it's just for the sake of the live stream. I'm not saying those sections aren't important. It's just for the sake of live stream. I want to keep audience engaged. I mean, like human characters. What if human characters? This is a math textbook. Okay. Oh, sorry, it was a joke. Okay. I got genuinely confused. Okay. So here, rigid motion. Rigid motion. Um, Hithyrtal. Is this word even used nowadays? My goodness. Hithyrtal, we have been discussing purely geometric quantities like vectors, involving points and line segments in 3D space. Now we wish to discuss motions, and thereby introducing a physical quantity, time. The concept of time is not a simple one. In relativity theory, time coordinates and position coordinates are intricably bound together, inextricably bound together. But for experiments involving only terrestrial objects with velocities much less than of light, hitherto probably rare these days, exactly, it is entirely satisfactory to use the Earth's rotation to define time. Wow, even time is defined. This, the subject matter of the book is highly applied, and the author even take the time to define what a time is. Just like how it take the time to define what a vector is in section 1. Okay. Anyway, it used by Avenger Endgame by Doctor Strange. Fair enough. So here, we're going to define time using the Earth's rotation in this section. How often do you see that? How often do you see that in any book? Raise your hand if you do. If you raise your hand if you find that pretty idiosyncratic. Let pi1 be the plane through the Earth's axis. Okay, let's draw the picture. Okay. Let pi1 be the Earth's axis. Be a plane through the Earth's axis. What do you mean by Earth's axis? Rotation axis, perhaps? Yeah, it says rotation axis. And passing permanently through some identifiable points of the Earth's surface. Passing permanently through some point. Okay, so it rotates along with the Earth, right? So let's just draw a picture. Imagine this is the Earth. And that's the meridian through Greenwich. Well, that was before an atomic clock, exactly. Yeah. Yeah. Exactly. So imagine this is a plane through the axis, Earth's rotation axis. You got the North Pole and the South Pole. Okay. And this meridian passes through Greenwich, for example. For example, the crosshair of the meridian circle at the Greenwich Observatory. Let pi2, this is pi1, okay, this is pi1. So pi1 rotates along with the Earth. And let pi2 be a plane passing through the Earth's axis at some distant star. Okay, so pi2 is fixed. So pi2 is fixed. I mean, yeah, nowadays, right? Nowadays you can every clock. Okay, so no, every clock is made of atom. Fair enough. Okay, you're funny. Fast track. So a distant star, like sun, for example. Okay, let's say a plane that's through the origin and the sun. So sun's location can be seen as relatively fixed. Relative to Earth, of course. Yeah. There's no need to retract the message, man. I'm not mocking you. Okay. I have to say, I find it funny. Okay. Thanks for cheering things out a little bit. I perhaps um, I'm too serious. Okay, sorry about that. Why do you guys keep retracting messages, man? Okay, I didn't even have time to read. Okay, perhaps that's the point. You don't want me to read it. That's why you retract it. But anyway, so here, this is pi 2. Pi 2 is a fixed plane, basically. Pi 1 rotates along the Earth. That's okay. That's okay. Don't feel bad about it. Pi 2 is fixed. The angle between pi 1 and pi 2 changes. Okay. So the angle between pi 1 and pi 2 changes. Good. I wasn't. No. You weren't polluting the conversation. I said I don't. Perhaps that was my own fault. Perhaps I made everything like super serious. Most of the time, this is a serious channel, right? Most of the time, but I don't want to be like super pedantic, and because this is internet after all, right? So okay, so here we have, in a good sense, okay. I don't want, this is it's the internet, and you don't expect the level of discussion to be high. This is what I'm saying. You expect to to be not always serious all the time on the internet. Okay, that's what I'm trying to say. So here you have pi 1 being a plane passing through the Earth's axis and some distance star. It's a fixed plane. The angle between pi 1 and pi 2 changes, of course, over time. A sidereal second, okay? A sidereal second is the time required for it to change this many revolutions. So basically, I think this is the reciprocal of the angular, what's that? For it to change. So a revolution is 2 pi. So revolution is 2 pi. So here, so-called one side second, one sidereal. Is that even a word? A sidereal second. Okay. So just treat it as 1 second. Is the time needed for Earth to perform 1 over 86,400 revolution. It's the number of seconds in a day. Yes, it does look familiar. Right. 86,400. That's the number of seconds in a day. Time needed. Time required for Earth to complete 1 over A6400 revolution. Due to the motion of the Earth in its orbit, the solar day, due to the motion of Earth in its orbit, I assume this is the Earth's orbit around Sun. The solar day between successive meridian crossings of the Sun is longer than the sidereal day. Yeah, like the sidereal year. Yeah. Between successive meridian crossings of a fixed star by roughly 4 minutes. On the average, enough to amount to 1 day per year. So a mean solar second is rough. Yeah, there was a. Yeah. So it went down again for some reason. Hey guys, is it okay now? How is now? How about now? Okay, great, awesome. Sorry. Yeah, it's just the internet is finicky. I hate to rant, but we pay so much. And perhaps it's the same in the States, but we pay so much for internet in North America. I mean, I live in Canada, and the quality is not very good. Anyway, let's come back to the main topic. As soon as we introduce different times into our considerations, we encounter the need of what may be considered pair splitting. Given a vector x at a time t naught and a vector of y at the same length at a different time t1, how can we tell if these are the same or different? I have two vectors of the same length at a different time. How can we tell if these are the same or different? Let's draw a picture. So let's just say you have x1, x, this is t equals t naught, right? And t1, x, this is at time equals t1. This is t2, t naught, my bad. X and y have the same length. That's the idea, no? Time t1. If t naught were equal to t1, the question would have an answer which is already given in section 1. What? I guess if you're comparing two vectors at the same time, how does comparing vectors have to do with time? Huh? Well, because in section 1 we do not have a notion of time yet, right? So if that's the same as comparing two vectors at the same time. But suppose we have A and B are two ends of a diameter of Earth. A and B are two ends of the diameter of Earth. Okay, and that at time, I suppose this is at, and that at time t naught, the line AB produces, and the line AB produced pass through a star S. Okay, let's draw the picture. So what's going on here? So imagine this is the Earth. You have two endpoints of the diameter of the Earth, and at time t naught, the line AB produced pass through the star S. Okay, so imagine I'm drawing the top-down view here. Okay, so this is, for example, say the North Pole, because AB are two ends of the diameter of Earth. Let's draw AB this way. This is AB. Line AB. AB passed through the star S. And this is time at t naught. This is time at t naught. So what's going on? Then at time t naught, we have AB divided by its own length equals AS divided by its own length. Yeah, that's true from the picture. Because AB divided by its own length is just the unit vector along the direction AB. And it's the same as the unit vector along the direction AS. And by the way, does changing the label, I mean, I put AB here purely for no reason, right? But what if we change the order of AB, does the conclusion change? Hopefully not. But let's just, if say B is here, A is here. You see, the conclusion fails here. AS over AS length points this way. The unit vector along AS points this way. Oh, actually it doesn't, no? It doesn't. It doesn't. Actually it does. It does. My goodness. What's going on? If we label AB the way I just did, okay. Can I erase that? Okay, so if let's say this is AB, this is the first way to label things. I want to pay attention to the second way to label things. If we exchange the order of AB, which is because this is arbitrary, right? I'm confused here. So let's just say AB is now exchanged. So unit vector along AB here in the first picture is the same as the unit vector along AS. They are the same. But here they're the opposite. It makes no sense. I guess we'll follow the part, or we'll follow the first convention. Because if you relabel AB, the conclusion fails. I don't think it does because you basically have two unit vectors. They should be the same. Yeah, but look at the picture though. If the order is ABS, then AB divided by AB length is pointing towards right. And also AS over AS length pointing towards right as well. But if you have BAS from left to right, then AB divided by AB length points towards the left, and AB divided by AS divided AS length towards the right though. Perhaps the line AB perhaps is a directed line. ABS. Only the first interpretation works. The second interpretation doesn't. Okay, we'll follow the first interpretation and keep pushing. But at another time t1, the points ABS will no longer be collinear, yes? So the two members of 1 will be unequal. So if we take the first interpretation, right? So S is still here. But now AB looks like this. A second instance. So this is A, this is B. I see what you mean. You're correct in saying changing the label changes the equation. Yeah. So apparently we're choosing one label. Okay. So here, but another time t1, this is at time t1. The points A, B, S will no longer collinear, like this diagram here. So the two members, what do you mean two members? The two vectors of AB, I say this is the direction along AB, unit vector direction along AB, and AS is this way, right? This is AS. They will form an angle in general. Will be unequal. The question is, which if either is unchanged. To one who is religiously convinced that the earth stands still, the answer is seemingly evident. The left member is unchanged. And to all of this, tacitly treat the left member as changing when we say the sun rises. Okay, this is quite ironic. I think this is a troll towards the people who think earth is fixed, huh? Okay, anyway. And all of this tacitly treat the left member as unchanging when we say the sun rises. It's not a complete sentence. And to all of us tacitly treat the left member as unchanging when we say the sun rises. Okay, reread the sentence. To one who is religiously convinced that the earth stands still, the answer seems evident. The left member is unchanged. Okay, and all of this, and as the left is unchanged. To all of this and all of this. What the hell? This sentence is not. This is a full sentence, but it does not look like a full sentence. Huh? All of us tacitly treat the left member as unchanging when we say the sun rises. This is not a full sentence. Actually, all of us is the subject, tacitly treated as a verb. The left member is unchanging when we say sun rises. Okay, right. Yeah. So when we say things like sun rises, you're using the Earth as a fixed reference frame. Okay, this is what it means. If S is a distant star, the astronomer would usually be willing to proceed as though the right member is unchanged. Yeah. So that's the picture here. This is the astronomer's point of view. We treat S as unchanged. You guys just lost the best game of the World Cup, Mexico versus England. Well, I have a schedule, don't I? So that's the cost. Oh, hi, Hiroshi. Good to see you again. At least I can watch the recording, I suppose. Mexico versus England. Thanks for bringing it up, though. Now I know what missed. Okay. Now I know what I missed. Okay. Before I didn't know. If S is a distant star, an astronomer would usually be willing to proceed as though the right member, namely AS, okay, here, AS is unchanged. You see, but still, look at the picture. It seems like AS and AB both changed. This is because S is so distant. S is so distant that A can be regarded as the center. Okay? So this is because the star is so far away that the radius of the Earth compares to the distance from the star to the Earth is so insignificant that this change in AS can be neglected. Okay, so that's the astronomer's convention here. This assumption is tacitly made whenever an astronomer determines the line by the meridian passes of a star. But an astronomer trying to determine the parallax of S will assume neither one is changed. Neither one unchanged. Okay. Hang on, what we're doing here? We're doing rigid motion, huh? Why is it? Okay, let's just keep going. I'm kind of struggling to see where this is going. But yeah, once, not so many decades ago, we might have tried to get out of this difficulty by regarding a vector as unchanging, okay, if at all times it joined the same 2 points of the ether. Okay, this is a physics notion now debunked. So remember, that's usually how it's usually taught in physics lessons, right? Newton assumed there's absolute space and time. There is an absolute stationary frame, right? And when Maxwell derived his equations, the Maxwell's equations, a consequence of that is that the speed of light can be predicted from electromagnetic theory. Right? So the speed of light in the vacuum is predicted using the magnetic and electric properties of medium. However, it is unclear what reference frame for that was, right? So people suspected Maxwell's equation only holds true for the absolute stationary frame. England won. Okay, my disappointment can't even be measured by measure theory. Yeah, England won. Pastor, are you Mexican? Just wondering. All right, but this is now a failed theory, basically. Ether is no longer considered a physically well-grounded theory. The Michelson-Morley experiment frustrates any such attempt. I'm Bosnian. Okay. So, wow, it must be very early, or is it very early in Europe now? Okay. Instead, we abandon all efforts to give absolute meaning to constancy of a vector or immobility of a point and find that we get along quite satisfactorily with a weaker substitute. Okay, what's the weaker substitute? Newton's country won. Math club is happy. Well, I'm pretty sure Bosnia has its own great mathematicians. I'm just perhaps ignorant about it. It's not like all British people are math people anyway. Anyway, so doesn't matter. I'm not even sure Newton likes football. soccer, whatever. Okay, so here, um, suppose that, what's the weaker substitute? Okay, what's the weaker substitute? Suppose that at each instance we choose three concurrent lines. Three concurrent lines. Okay, let's draw a picture. Suppose that at each instant we choose three concurrent lines. Do they have any particular requirement? I don't know. Let's not be special here. Could you just say this is okay, OX1, OX2, OX3. Three concurrent lines in three space, I suppose. Since the angle between OX1 and OX2 is a real number, okay, this angle here is a real number, no trouble arises if we require that this angle have the same value for all time t. No trouble arises if we require that this angle have the same value for all times t. Okay? Suppose that at each instant we choose three concurrent lines. Since the angle between OX1 and OX2 is a real number, no trouble arises if we require that this angle have the same value for all time t. Huh. Okay. Likewise, for the angle between OX1 and OX3 have the likewise for the angle between OX1 and OX3 and the angle between OX2 and OX3. Yeah, so this is like a coordinate axes, right? This is a set of coordinate axes. For present purposes, the manner in which the lines are chosen is unimportant. But in specific applications, they will always be chosen as some recognizable lines related to a material object, for example, the Earth. Okay, that's a coordinate frame of reference or coordinate system. And we can introduce coordinate vectors k1, k2, k3 as before. Okay, so we need to go back. Where was things like k1, k2, k3 mentioned in the earlier part of the text for each separate instance of time? Okay, now we can say that a point is fixed with respect to O, x1, x2, x3 system if each of its three coordinates remains a constant value at all time. Well, won't be the point that AS and BS differ by more than sine BS over 2, or expect if you just measure the angular position of the circumference. Oh, you're talking about this diagram here? F? Okay, anyway, okay, so ignore that. So let's go back to the definition of K1, K2, K3 in the earlier part of the work. Do we see any K1, K? Okay, I see K. Do you have K1, K2, K3? Yeah, K1, I can see. It seems like to be the unit vector. For example, this is obviously a derivation of the cross product identity. So K1 and K2, let me just check if my understanding is correct. Hopefully they are the unit vectors. Yeah, K1, K2, K3. This is a, yeah. So unit vectors K1, K2, K3 from a right-hand set. Components of vectors. If K1, K2, K3 are three linearly independent unit vectors, we may use them to define a coordinate system. Okay. Okay, so these are unit vectors. They don't have to be orthogonal, no? Do they have to be orthogonal in this convention? Well, did we use things like k1 dot k2 equals 0? Does it say? Just linear independent. Yeah, it just says linear independent. Exactly. It can be, so in principle it can be oblique, right? And here in our discussion about time dependent coordinate system. Here, this is a discussion about time dependent coordinate system. They just say, it just says that the coordinate axes form fixed angles. It doesn't say have to be orthogonal. Okay? So we can use these lines as axes of a coordinate system, and we can introduce coordinate vectors k1, k2, k3 as above. So these are just unit vectors. Unit vectors are linearly independent for each separate instance of time. Now we can say that a point is fixed relative to the coordinate system if each of these three coordinates retains a constant value at all time. And we can say that a vector x is a constant vector. A vector x is a constant vector relative or with respect to the coordinate system if each of its three components retains a constant value. Okay, makes sense. Can be oblique. How is that possible to form? Yeah, it can be, right? This is called an affine coordinate. Doesn't have to be orthogonal. Right? So basically, it's a fact from linear algebra is that as long as you have linear independent bases, well, bases or by definition is linear independent. I'm trying to say is as long as you have a set of linearly independent vectors that spans the whole space, then every vector in that space can be written as a unique linear combination of such vectors. And the coefficients of the linear combination is called coordinate. Right? So a coordinate is then well defined. Okay, the coordinate is well defined. This way, it is a valid coordinate system. So coordinate system can totally be oblique. Right. I guess this is all to say that Galilean relativity is a thing, and therefore it's all good. I suppose. I mean, it's said straight from the beginning we're not going to do Einstein's relativity here. It's okay. Um, I think nobody uses Einstein's theory in ballistics. But won't some not be unique unless also orthogonal? I'll look into thank you. No, this is just a fact from linear algebra. Actually, you know what? Let's go back to the previous part. Coordinates and vectors. To define coordinates, you just need linear independence. You don't need orthogonality. Yeah, this is a basic fact from linear algebra, but let's review that. Yeah, if x1, x2, x3 are linearly independent, i.e. non-coplanar vectors, every vector z in three-dimensional space can be represented in exactly one way as a linear combination of them. What about ballistics for particle colliders? Well, yeah, you would have to worry about relativity, for sure. You got me there. Okay, so to prove the last statement is quite straightforward. Right? You suppose there are two such representation. You suppose there are two such representation, and then you subtract the equations, and you get a linear combination of x1, x2, x3 equals 0. But by linear independence, the three coefficient must be 0. The difference between the three coefficients must all be 0. So therefore, the representation is unique. Yeah, that's okay. Totally okay though. Because this is how we catch our vulnerability in our foundation. Right? The set of coordinate axes don't have to be orthogonal. All right. So in physics, a particle is ordinarily understood to mean a material object whose dimensions are too small to be of significance in a particular problem under discussion and whose spatial orientation is also of no significance. Wow, even defines a particle. I like it. All right, so this obviously is meant to guide the discussion about the flight of a projectile, whether or not a projectile can be seen as a particle. So in last week's stream, we did use a particle model to solve a differential equation, right? We to formulate a differential equation and then solve it. So I was discussing the flight of a subsonic projectile. A subsonic projectile has this drag law. Basically, the drag is proportional to speed squared, and we derive the approximate analytic formulas for calculating the range table for example, a classic pistol caliber round. Right? So over there, we use the particle assumption, and that's actually still the most dominant method today, especially in modern small arms. Okay, in modern small arms, you typically still use the particle model. So it's just 3 degrees of freedom. You don't worry about the rotation, precessions, and whatnot of the particle of the projectile. But for long range shooting, this is important because you have the barrels are typically rifled. The barrels are typically rifled to ensure stability. To study stability, you'll have to understand rigid body mechanics, so which is a 6 degrees of freedom. So to specify the state of the configuration of a rigid body, you need 6 degrees of freedom. So 3 for translational coordinates or translational motion, and 3 for rotational motion. And nowadays, the most advanced ballistic simulations uses 6 degrees of freedom. For example, for artillery rounds, the numerical method, if for howitzers or self-propelled artillery, so to say, you would use 6 degrees of freedom. So here, we'll get to that in a later part of the book. So in physics, a particle is ordinarily understood to mean a material object whose dimensions are too small to be of significance in a particular problem. Under discussion, whose spatial orientation is also of no significance. Such a particle can then be regarded as merely an identifiable point of space, whose position with respect to a chosen coordinate system, OX1, x2, x3, is given at any time t by 3 coordinate functions. Right? So 3 coordinate function x1 of t, x2 of t, and x3 of t. Typically in physics, you write x, y, and z. The velocity vector, velocity v, at time t0 of the particle with respect to the coordinate system is defined as follows. Okay, so that's once again very standard definition of a velocity, just a derivative vector function. Let pt be the position of the particle at time t. So let's draw the picture right next to it. So imagine pt is a function of t. pt is a trajectory. Okay? As t changes, position changes, you get a trajectory. The trajectory of the particle at time, the trajectory of the particle, and which we denote as pt. P0 be the point which is fixed with respect to the coordinate system and which coincides at time t0 with p. So here, p0, you can think of that's the original position. This is the position at time t0. And then you divide the vector. Divide the vector p0 pt by the time difference, provided the limit exists. Okay, suppose this is, say, the origin, right? So you would calculate this vector difference divided by the time difference. And that's the definition of vector. Definition of a velocity vector. All right, so you can write it in component form. And each component, vi, is xi dot. I suppose everyone is familiar with the dot notation for derivative, especially for time derivative. This is a standard in physics. Time derivatives are used as dot. So this permits us to write v equals x dot, where we must keep in mind that neither side of the equation has any meaning except with reference to some specific coordinate system. Exactly. Velocity is a coordinate dependent object. And if x1, x2, x3 are the components of x in a coordinate system with coordinate vectors k1, k2, k3, then you can write it in component form. Those has always time derivative in physics. Yeah. X dot. I think this is due to Newton, huh? X dot notation. X double dot is due to Newton. Okay. The velocity v of a particle should be carefully distinguished from its speed. Yeah. So speed is just the length of the vector, which by definition is the absolute value of its velocity or the length. Thus, properly speaking, an airplane cannot have a velocity of 300 miles per hour with respect to, say, to the ground. It can have a speed of 300 miles per hour. All right? The speed is a number. That's the, I think, yeah, it's the Fluxion notation. Very cool. So, so in ballistics, we often talk about the muzzle velocity of a firearm, of a projectile. It's perhaps better to say muzzle speed. Okay, it will have a speed if its velocity is 300 miles due west and horizontal. Sure. Okay, if OX1, X2, X3 is another coordinate system, a point P naught fixed with respect to a new system may have velocity W. Yeah, that's totally possible, right? And if you use a different coordinate system, the velocity of a point may change. That's why when you're sitting on a bus and the bus is driving forward, it feels like everything is going backward. Right? So it's just different coordinate system. Moreover, this velocity w may vary with the point p naught and with time t. Yeah, non-constant velocity at different locations. This can totally happen. It will be called the velocity at time t and place p naught of O star x star O star x1 star x2 star x3 star system with respect to the original system. In order to avoid repeated restatement of a hypothesis, we should always assume when changing from one coordinate system to another that the velocity of the new system will with respect to the old one exists. We rule out non-differentiable motions. So you assume motions are smooth, and you can always do change of coordinate transformation. Okay, makes sense. A particle P which has a velocity v with respect to the old system will ordinarily have a different velocity with respect to a new system. Okay, so now you get, yeah, this is Christian was saying this is the velocity addition rule for the Galilean transformation. Brownian motion is so sad. Yes, exactly. You don't want your projectile motions to be Brownian, don't you? Right. So, so I think this is quite familiar to everyone. The good old velocity addition formula in classical mechanics. So suppose your W is the velocity of a moving frame relative to a fixed frame, quote unquote fixed frame, okay? And then the velocity in two frames are simply related by a simple vector addition. Okay. And here's a proof. Okay. It even proves that. Okay, very nice. Freaking mosquito in my room. Yeah, anyway, here, I think, don't give them ideas. Yeah, you're right. I wonder though, because um, I wonder if stochastic calculus have uses in exterior ballistics. Probably, huh? You know what? Let's just Google it right now. Not in this book, obviously, but for some reason, McShane, yeah, the first author, McShane, also wrote a book on stochastic calculus. So let me just ask Google real quick. Is stochastic calculus used in exterior ballistics? I'm not sure. Yes, actually, it is used in. It is used in. Oh wow, exterior ballistics. I see my stream is in the Google search result. Okay, so here that's the yeah. Apparently it has used in advanced trajectory modeling, submunition dispersion analysis, and weapon effectiveness. While standard point mass, yes, I was talking about the point mass or a particle, and 6DOF ballistic calculator rely on deterministic differential equations. Real world flight involves unpredictable variables. Okay, things like atmospheric variability, manufacturing tolerances, target uncertainties. Using stochastic calculus, engineers and physicists can move beyond predicting a single idealized trajectory. Instead, they calculate the probability density functions of impact points to determine metrics like circular error probable, CEP, and probability of kill. Wow, that's brutal. PK, probability of kill. Because closed form solutions at SD are too complex. These models frequently solve using numerical methods like Monte Carlo simulation. Oh, that's crazy. Let's take a look at this paper. Stochastic ballistic model for calculating engagement probability. I guess that's the probability of hit for multiple weapon system. That escalated quickly, exactly. My goodness. Where's the math? A projectile using six-dimensional state vector. Okay, so this is a particle model, x, y, and z, and their velocities. My, to capture uncertainty in the system, we augment the deterministic dynamics with stochastic forcing. The resulting Ito stochastic differential equation is this. Well, there you go. After watching the stochastic calculus series on the channel, you can read this paper. Diffusion model, impact point, mean and covariance of the impact distribution, circular error probable, integration with lethality. Let F be any measurable lethality kernel that maps its impact location to conditional kill probability after accounting for relevant factors such as target vulnerability, warhead characteristics, etc. Damn, bro. See, you actually do discretize this SDE and solve the stochastic differential equation. The definition of probability of a kill. Man. Example 1. Unguided artillery shell. Okay? The stochastic model in this case, blah, blah, blah. You have some, yeah. So battery 152 millimeter howitzer providing fire support for an infantry assault across open terrain. The target is a stationary enemy command post or supply depot 15 kilometers away. The projectile is subject to, you know what, let's put that link in the chat so you guys can read it at your own pace. Okay. And at the same time, okay, contemplate on the moral consequence of this sort of modeling. Okay. So here, the target is a stationary enemy command post or supply depot 15 kilometers away. The projectile is subject to a velocity. Okay, you have variations in the velocity. I guess the speed. The projectile is subject to muzzle velocity variation. Sigma v is 5 meters per second. Are we the baddies? Good question. Due to barrel wear and propellant temperature, with unpredictable crosswind from a nearby hill or passing vehicles modeled by Gaussian wide correlation noise. No guidance system or control inputs are used, only standard ballistic tables. The stochastic model in this case, blah blah blah, and you can simulate. Assume the lethal radius is 15 meters, then the kill probability for isotropic Rayleigh distance is, the kill probability is 67%. Damn, bro. Simulations for ns equals 10 to the 5. So basically, for an SDE, you would simulate the trajectories. So here it says you simulate 10 to the 5 Monte Carlo trajectories. Okay, no worries, Christian. Thank you very much for joining the stream. My God. So you actually simulate the trajectories and estimate the probability to be... Oh, wow. Oh, so this is a simulation, then that's the theoretical result. Turns out to be quite close, huh? Confirming agreement with analytic approximation. Under normal wind and barrel condition, you can expect roughly 2/3 of a round to hit within lethal range of a point targeting 15 kilometers. This is satisfactory for area suppression, but risky against hardened bunkers. Example 2, guided missiles with multiplicative noise. Damn, bro. That escalated super quickly. Surface to air missile with stochastic targeting maneuvers. Rocket artillery with strong wind coupling. Precision guided munition. Analytic approximation error bounds. Linearization and Gaussian approximation. Applying the Ito's lemma. This is covered in the channel, no? This is a numerical scheme, the errors in the numerical scheme. The error bounds in the Monte Carlo simulation. Edgeworth expansion. By the way, this is a super cool asymptotic technique in statistics, by the way. Edgeworth expansion. You can think of it as an extension of the central limit theorem. Throughout the illustrative examples, motion of moving targets explicitly models an Ornstein-Uhlenbeck process. By the way, this is one model for the Brownian motion. No, this is one model for Brownian motions in a potential field. Damn, bro. By contrast, a worst-case adversarial formulation would treat the target as an intelligent opponent that chooses its control input U to minimize success, so that the probability of kill would be calculated or estimated as P kill worst. P kill worst. So basically, you mean the target is now an intelligent opponent. It will chooses an action U. This is the control function, okay, that try to minimize the function, minimize the probability of being killed. So that's the infimum of the kill probability over the possible choice of control, where big U is a set of admissible target strategies. And we interpret this value as the guaranteed single shot probability that holds even against the most evasive possible maneuver. Damn, bro. Direction for further research. Non-Gaussian stochastic models, coupled guidance estimation models, game theoretic targeting modeling, rare event simulations. This is the Python code. Like, what do you guys feel about this? Type it in chat. And it's the link is in chat. All right. I think it's a good time for me to stop today because I had a big day. Our church had a outdoor worshiping event today, and I'm completely exhausted. I love applied math. Do you though? I don't know what I should feel about applied math after seeing all of that. I feel, I mean, I don't feel complicit, but I think the community, I feel complicit about the community, about the applied math community. Right. Should I make a video about it as a bonus, so to say, a bonus video on stochastic calculus? Maximizing and minimizing the expected maximum likelihood. That's you already know they're using cameras to better predict the specific movement too. Yeah. So this is very concerning. Let's just put it that way. It does sound super interesting. It is. It's morbid, but it's interesting, right? Anyway, I should probably end the stream because I'm getting super tired. Thanks again, everyone, for joining the stream. And okay, I'll say yes. Okay. Okay. Perhaps as a bonus video, other than the more standard applications of uh, option pricing, common filters, and whatnot. Good night.